For most of human history, the Andromeda Galaxy was nothing more than a faint smudge in the night sky. Some called it a nebula, a mere pocket of gas within our own Milky Way. Others dared to dream bigger, suspecting it might be an entire galaxy in its own right. The truth, once revealed, shattered our understanding of the universe. Andromeda isn't just another celestial object, it's the largest galaxy in our local group, home to 1 trillion stars and untold mysteries. But Andromeda is also our future. In a cosmic ballet playing out over billions of years, our galaxy and Andromeda are on a collision course, destined to merge into something entirely new. What secrets does this galactic neighbor hold? Could it be home to planets we have yet to discover? And one day, could humanity, or something we create, travel across the intergalactic void to reach it? Nebula or galaxy? The 20th century debate. In the early 20th century, astronomers faced a question that would change our understanding of the universe. Was the Andromeda Nebula just another cloud of gas within our Milky Way? Or was it an entirely separate galaxy, like our own but unimaginably far away? At the time, the universe as people understood it was much smaller. Most scientists believed that the Milky Way contained everything, every star, every planet, and every cloud of gas. When telescopes revealed faint glowing patches of light in the night sky, astronomers classified them as nebulae, assuming they were clouds of interstellar material, perhaps forming new stars. Andromeda was one of these mysterious objects, a spiral-shaped patch of light that stood out among the many other nebulae catalogued in the sky. The debate over Andromeda's true nature intensified in the early 1900s. Some astronomers argued that it was a separate system of stars, an island universe of its own. This was a radical idea. If Andromeda was a galaxy, then the universe was far bigger than anyone had imagined. It would mean the Milky Way was not alone, but one of countless galaxies scattered throughout space. One of the strongest arguments against Andromeda being a separate galaxy was the belief that the Milky Way was vast enough to encompass everything. In 1917, astronomer Harlow Shapley estimated the size of the Milky Way and concluded that it was about 300,000 light-years in diameter, an enormous size by the standards of the time. If Andromeda were outside the Milky Way, it would have to be millions of light-years away, a distance that seemed almost impossible to accept. Shapley and others who shared his view believed that all known nebulae were part of our galaxy, and that the idea of other galaxies was unnecessary. Opposing this view was Heber Curtis, another respected astronomer. He pointed to certain observations that suggested Andromeda might be far beyond the Milky Way. One major clue was the presence of novae, exploding stars that briefly shine brightly before fading away. Curtis found that novae in Andromeda appeared much dimmer than those observed in the Milky Way. If they were indeed the same type of event, then the only explanation was that Andromeda was much farther away than previously thought. Curtis also noted the structure of Andromeda itself. It had a spiral shape, much like other mysterious spiral nebulae observed in the sky. If these spirals were simply gas clouds within the Milky Way, it was unclear why they had such distinctive, ordered structures. If, however, they were separate galaxies, their spiral shapes made more sense. They were vast collections of stars, much like the Milky Way itself. This scientific disagreement came to a head in 1920 at a historic meeting known as the Great Debate. Shapley and Curtis publicly argued their positions at the Smithsonian Institution, each presenting their evidence for and against the idea that Andromeda was a separate galaxy. Shapley defended the idea of a single galaxy universe, arguing that the Milky Way was so large that there was no need to consider other galaxies. Curtis, on the other hand, insisted that Andromeda and other spiral nebulae were independent star systems. The debate itself ended without a clear winner. Both men presented strong arguments, and there was no definitive evidence to settle the question. However, the search for an answer continued, and within just a few years, the mystery of Andromeda would finally be solved. In 1924, Edwin Hubble made a groundbreaking discovery using the 100-inch telescope at Mount Wilson Observatory in California. At the heart of Hubble's work was a type of star known as a Cepheid variable. These stars pulsate in a steady rhythm, growing brighter and dimmer over time. Earlier in the century, astronomer Henrietta Swan Leavitt had studied Cepheids and discovered a key relationship. The longer a Cepheid's pulsation cycle, the more luminous it is. This meant that if astronomers could measure how fast a Cepheid varied in brightness, they could determine its true luminosity. Comparing this with how bright it appeared from Earth allowed them to calculate its distance. When Hubble calculated the distance to Andromeda, the result was shocking. It was over 2 million light-years away. This placed Andromeda far beyond the boundaries of the Milky Way, proving once and for all that it was a separate galaxy. Hubble's discovery transformed astronomy overnight. No longer was the Milky Way the entirety of the universe. It was just one of many galaxies, each containing billions of stars. The debate that had raged for decades was finally settled. The idea of an island universe was no longer just a theory. It was a reality. This revelation opened the door to even greater discoveries. As telescopes improved, astronomers found more and more galaxies stretching across the universe, some much larger than the Milky Way. The realization that our galaxy was just one of many led to new questions about the universe's size, structure, and origins. The field of cosmology expanded rapidly, moving beyond the simple study of the Milky Way to an exploration of the universe as a whole. Shadows of doubt, unresolved early observations. Even after Edwin Hubble's discoveries reshaped astronomy, doubts and unanswered questions remained. Science rarely moves in a straight line, and the confirmation that Andromeda was a galaxy did not erase all uncertainty. Some astronomers hesitated to fully embrace the new model of the universe, and certain early observations seemed inconsistent with the idea of multiple galaxies. One of the biggest lingering concerns involved the brightness of galaxies. If they were actually millions of light-years away, their true luminosity had to be far greater than anyone had expected. Some scientists found it difficult to believe that individual galaxies could shine so brightly across such vast distances. It was a challenge to explain how these enormous structures generated so much light, especially when astronomers still did not fully understand the energy processes inside stars. At the time, the dominant theory of how stars produced energy was still being debated. The idea that stars relied on nuclear fusion to sustain themselves was not yet fully established. In the early 20th century, many scientists still believed that stars might shine due to gravitational contraction, slowly compressing under their own weight to generate heat. However, this process could not explain how stars maintained their brightness for billions of years. If galaxies contained billions of stars, as Hubble's work suggested, then a new understanding of stellar energy production was needed to account for the amount of light emitted. This issue was not resolved until the mid-20th century, when researchers confirmed that stars were powered by nuclear fusion, converting hydrogen into helium in a process that released vast amounts of energy. There were also questions about the distribution of galaxies. If the universe contained countless galaxies, why did they appear concentrated in certain regions, while other areas seemed nearly empty? Some surveys of the sky showed clustering patterns that did not immediately make sense. Early observations suggested that galaxies were not randomly scattered, but instead seemed to form groups and clusters. Some astronomers wondered whether this was an illusion caused by the limitations of telescopes, while others suspected it was a fundamental feature of how galaxies were arranged. If galaxies were forming groups, what force was responsible? Gravity seemed like the obvious answer, but scientists did not yet have the tools to fully study the large-scale motions of galaxies. Another source of doubt came from early attempts to measure the movement of galaxies. Hubble had shown that galaxies were receding from us, but some astronomers found odd exceptions. A few galaxies seemed to have very little redshift, suggesting they were not moving away as fast as others. Even more strangely, Andromeda itself appeared to be moving toward the Milky Way, not away. If the universe was expanding, why was this massive galaxy on a collision course with our own? The explanation, as scientists later realized, was that the overall expansion of the universe did not prevent local galaxies from having their own motions due to gravity. Andromeda and the Milky Way were close enough that their mutual gravitational pull dominated over the cosmic expansion, drawing them together. Hubble had confirmed Andromeda's vast distance, but what about the many other spirals catalogued in the sky? Were they all as far away as Andromeda, or were some actually within the Milky Way? Astronomers had to carefully examine each object to determine its true nature. In some cases, what appeared to be a spiral nebula was later found to be something different, like a planetary nebula or a supernova remnant within our own galaxy. The distinction between galaxies and other celestial objects was not always obvious. If galaxies were enormous systems of stars, how did those stars form? And did all galaxies create stars at the same rate? Early observations showed that some galaxies appeared more active than others, but the reasons were not well understood. Some galaxies had bright glowing regions that seemed to indicate intense star formation, while others looked more subdued. Scientists needed more data to determine what was driving these differences. If galaxies were separate systems, had they always existed in their current forms? Did they change over billions of years, or were they static structures? The light from distant galaxies took millions or even billions of years to reach Earth, but telescopes were not yet powerful enough to see far enough back in time to study the earliest galaxies. Scientists could only observe the galaxies available to them and make educated guesses about their past. Even with all these uncertainties, the idea that Andromeda was a galaxy became widely accepted. The evidence in its favor was too strong to ignore. But every answer led to new mysteries and showed that the study of galaxies was only just beginning. Unraveling Andromeda's intricate composition. Andromeda, also called Messier 31 or M31, eventually became one of the most studied galaxies in the universe. As astronomers moved beyond the question of whether it was a galaxy, they turned their focus to understanding its structure, composition, and hidden complexities. What they found was a vast system filled with billions of stars, swirling clouds of gas, mysterious halos of dark matter, and a history of galactic mergers that shaped it over billions of years. Like the Milky Way, Andromeda contains stars of all ages, from young blue giants to ancient red dwarfs that have burned for billions of years. In its bright central region, older red stars dominate, suggesting a long history of stellar evolution. These stars formed early in the galaxy's life, using up much of the available gas. But in its spiral arms, where dense clouds of gas and dust still linger, younger stars are constantly being born. These regions glow with the light of hot blue stars that have formed relatively recently in astronomical terms. A galaxy filled only with old stars would suggest it had stopped forming new ones long ago, while a galaxy packed with young stars would imply it was still in the early stages of development. Andromeda, however, is a mix of both, meaning it has gone through cycles of star formation, sometimes creating bursts of new stars, while at other times remaining quiet. These cycles are driven by the movement and interaction of gas, which serves as the raw material for new stars. Andromeda's vast reservoirs of gas and dust provide clues about how the galaxy continues to evolve. Hydrogen, the most abundant element in the universe, makes up much of the gas within the galaxy. Large clouds of hydrogen float between the stars, sometimes gathering into dense regions where gravity pulls the material together. If enough gas collects in one place, the pressure and temperature rise until nuclear fusion ignites, forming a new star. In some regions, entire clusters of stars are born from a single massive gas cloud. Some of the gas does not match the movement of the rest of the galaxy, suggesting that Andromeda has absorbed smaller galaxies over time. When a small galaxy drifts too close, Andromeda's gravity pulls it in, stripping away its stars and gas, adding them to its own structure. These galactic mergers have left behind faint streams of stars and disrupted patterns of gas, signs of past collisions. Surrounding the galaxy is an enormous halo of invisible material that does not emit or reflect light. This hidden substance, known as dark matter, is thought to make up most of Andromeda's mass, yet it remains undetectable except through its gravitational effects. Astronomers first suspected the presence of dark matter when they studied how galaxies rotate. In a typical system, the stars and gas at the edges of a galaxy should orbit more slowly than those near the center, much like how planets in the solar system move slower the farther they are from the Sun. But observations showed that Andromeda's outer stars were moving just as fast as those closer to the core. The only explanation was that some unseen mass was providing extra gravity, holding the stars in place. By studying the motion of stars and gas, scientists estimated that Andromeda contains far more dark matter than normal matter. The visible stars, gas and dust account for only a fraction of the galaxy's total mass. The rest is locked away in this invisible component, forming a massive halo that stretches far beyond the galaxy's main disk. This dark matter is thought to form a kind of cosmic scaffold, shaping the growth and evolution of galaxies. But despite decades of research, its exact nature remains unknown. Andromeda's structure also includes a bright central bulge, a thick disk of stars, and extended spiral arms. The core of the galaxy is densely packed with older stars, surrounding a supermassive black hole at the center. This black hole is millions of times the mass of the Sun, though it appears to be less active than some found in other galaxies. It does not consume large amounts of material, meaning it does not produce the powerful jets and radiation seen in more energetic galaxies. Moving outward from the core, the thick disk of stars extends across a massive region, with spiral arms curving outward in a familiar pattern. These arms are not solid structures, but instead consist of waves of density that move through the galaxy, triggering star formation as they pass through clouds of gas. Over time, these arms shift and change, influenced by the gravitational pull of Andromeda's many smaller satellite galaxies. Andromeda is surrounded by dozens of smaller galaxies that orbit it like moons around a planet. These include dwarf galaxies such as M32 and M110, which are gradually being torn apart by Andromeda's gravity. Some of these smaller galaxies may eventually merge completely, adding their stars and gas to Andromeda's growing structure. The galaxy is also home to a vast population of globular clusters, dense groups of tightly packed stars that orbit around the central region. These clusters contain some of the oldest stars in Andromeda, remnants from its earliest days. Studying these clusters provides insight into how galaxies form and evolve over time, as they serve as ancient records of the conditions that existed billions of years ago. Recent studies of Andromeda have revealed even more unexpected features. Astronomers discovered a vast, thin plane of dwarf galaxies orbiting the main galaxy in a coordinated pattern, a structure that challenges current theories of how galaxies form. The reason for this alignment is still unclear, as simulations suggest that satellite galaxies should be randomly distributed rather than arranged in a flat plane. Another surprising find is the discovery that Andromeda has experienced at least one major merger in its past. While the Milky Way has grown mostly by absorbing smaller galaxies, Andromeda appears to have collided with a larger system at some point in its history. This ancient merger reshaped the galaxy's structure, scattering stars and gas across vast distances. The evidence for this event comes from the motion of stars in Andromeda's outer halo, where remnants of a past galaxy still linger. As the closest large galaxy to the Milky Way, Andromeda serves as a cosmic laboratory for understanding how galaxies work. Scientists are still working to determine how its supermassive black hole affects the surrounding stars, and how its satellite galaxies interact with its larger structure. New telescopes and instruments will provide even deeper insights, allowing astronomers to map the galaxy in greater detail than ever before. The Cosmic Palette, Andromeda's unique chemical fingerprints. Just as a forensic scientist studies traces of material at a crime scene, astronomers examine the light from Andromeda to determine what elements make up its stars, gas, and dust. This chemical fingerprint is unique, shaped by billions of years of stellar evolution, collisions, and cosmic recycling. The most common element in Andromeda, as in the rest of the universe, is hydrogen. It is the simplest and most abundant element, forming the primary fuel for star formation. Alongside hydrogen, helium is also present in large amounts, produced in the early moments of the universe during the Big Bang. These two elements form the building blocks of stars, but what makes Andromeda chemically unique is the heavier elements that have been forged within its stars over billions of years. As stars go through their life cycles, they create new elements through nuclear fusion. Lighter elements such as carbon, nitrogen, and oxygen are formed in smaller stars, while heavier elements like iron, nickel, and gold emerge in more massive stars and explosive supernova events. These newly formed elements are released into space when stars die, mixing into the surrounding gas and dust. This cycle continues as new generations of stars form from enriched material, each one containing a slightly different chemical makeup than the last. The chemical diversity in Andromeda is not uniform. The oldest stars in the galaxy's halo, which formed billions of years ago, contain fewer heavy elements compared to the younger stars found in the spiral arms. This is because these early stars formed before many of the heavier elements had a chance to accumulate. In contrast, the spiral arms, where new stars continue to form, are rich in metals. Astronomers refer to all elements heavier than helium as metals, indicating that they have been enriched by multiple generations of stellar activity. One of the most striking chemical features of Andromeda is the presence of unusual isotopic ratios. Isotopes are different forms of the same element, containing the same number of protons but varying numbers of neutrons. Certain isotopes, such as those of oxygen and carbon, provide valuable clues about the processes that have shaped the galaxy. Scientists have found differences in these isotopic ratios when comparing Andromeda to the Milky Way, suggesting that the two galaxies have had different evolutionary paths. These variations can be traced back to the types of stars that contributed to Andromeda's chemical makeup. Some isotopes are produced in the intense heat of massive stars, while others are formed in slower-burning, smaller stars. By analyzing the distribution of these isotopes, astronomers can determine which kinds of stars played a dominant role in shaping Andromeda's composition. The patterns they have observed suggest that Andromeda has experienced a different rate of star formation and possibly different kinds of stellar explosions compared to the Milky Way. When a galaxy merges with another, it not only absorbs stars, but also gains any unusual chemical signatures carried by the incoming system. Some of Andromeda's outer regions show signs of elements that do not match the typical composition of its main disk. These could be remnants of long-lost galaxies that were absorbed by Andromeda, leaving behind traces of their unique chemical identities. The core of the galaxy contains a higher concentration of iron and other heavy elements compared to the surrounding areas. This suggests that Andromeda's core may have undergone intense periods of star formation and supernova activity in the past. Some of these elements could have been created in short-lived massive stars that exploded violently, enriching the surrounding space with heavier elements. This process is similar to what has been observed in other galaxies with active star-forming regions. Some studies have suggested that Andromeda has a slightly lower abundance of certain elements, such as magnesium, compared to what is expected for a galaxy of its size and age. This could be a sign that Andromeda's chemical evolution was influenced by external factors, such as variations in its early environment or past interactions with other galaxies that altered its star formation history. Dust grains, composed of tiny solid particles of carbon, silicon, and other elements, are scattered throughout the galaxy. These dust particles play an important role in the formation of new stars and planets, as they provide the raw materials needed to build planetary systems. The chemical composition of this dust varies across the galaxy, with some regions containing more carbon-rich grains, while others are dominated by silicates, similar to the rocky materials found on Earth. One of the key tools scientists use to analyze Andromeda's chemical fingerprints is spectroscopy. By studying the light emitted or absorbed by different elements, astronomers can determine the precise composition of the galaxy. This technique has revealed the presence of molecules such as carbon monoxide, which is often found in dense clouds where new stars are forming. The detection of these molecules helps researchers understand how Andromeda continues to evolve and produce new generations of stars. As the galaxy continues to form stars, its overall metallicity, the abundance of elements heavier than helium, will increase. However, as its supply of raw gas slowly depletes, the rate of star formation will decline. Eventually, Andromeda will become a galaxy dominated by older stars, with fewer new ones being born. When it eventually merges with the Milky Way in about 4 billion years, the combined galaxy will carry the chemical fingerprints of both systems, blending their histories into a new cosmic identity. Hidden luminaries, rare stars of Andromeda. Andromeda is home to an immense variety of stars, many of which follow predictable life cycles and match what astronomers see in other galaxies. However, scattered among these common stars are some rare and unusual types. Some of them are remnants of violent cosmic events, while others are still forming in ways that challenge current models of stellar birth. One of the most intriguing groups of rare stars in Andromeda is the population of luminous blue variables. These stars are massive, unstable, and prone to sudden changes in brightness. They exist in a delicate balance between gravity and radiation pressure, with their outer layers frequently being blown away by strong stellar winds. One of the best-known examples of a luminous blue variable in Andromeda is AE Andromedae, which has been observed to fluctuate in brightness over time. These stars are thought to be in a short-lived phase of evolution before they explode as supernovae, making them key targets for understanding the final stages of massive stars. Scattered throughout Andromeda's spiral arms are a number of Wolf-Rayet stars, a rare and extreme category of hot, massive stars nearing the end of their lives. These stars have already lost most of their outer hydrogen layers, exposing the deeper, hotter regions where heavier elements are being formed. Because of this, Wolf-Rayet stars emit strong stellar winds and shine with an intense blue-white light. Their presence indicates regions of recent star formation, as they only live for a few million years before collapsing in dramatic supernova explosions. Then there are Andromeda's hypervelocity stars, stars moving at extraordinary speeds that should not be possible under normal conditions. Some of these stars may have been ejected from binary systems when their companion exploded as a supernova. Others could have been flung outward after a close encounter with Andromeda's supermassive black hole. These hypervelocity stars travel so fast that some may eventually leave the galaxy entirely, carrying with them clues about the extreme gravitational forces at play within Andromeda. In the outer reaches of the galaxy, a different kind of rare star lurks: carbon stars. These stars have an unusual abundance of carbon in their atmospheres, which gives them a distinctive reddish glow. Carbon stars are thought to form when convection within the star dredges up carbon from deeper layers, enriching the outer atmosphere. This process changes the way the star emits light, making it appear redder than normal. Andromeda's carbon stars are particularly interesting because they hint at how chemical elements are recycled in galaxies over time. These stars shed carbon-rich material into space, helping to enrich the interstellar medium with the raw materials needed for future star and planet formation. Deep in Andromeda's central bulge, astronomers have found an unusual population of extremely metal-poor stars, stars that formed in the early history of the galaxy, when heavier elements were still scarce. These stars are relics from a time when the universe was much younger, and their compositions provide a glimpse into what conditions were like billions of years ago. Because they contain so few heavy elements, they are believed to be some of the oldest stars in Andromeda, possibly dating back to the time when the galaxy was just beginning to take shape. Yellow supergiants are stars that are caught in a brief transition phase between being red supergiants and blue supergiants, making them difficult to observe. Yellow supergiants are rare because their evolutionary phase lasts only a few thousand years, a mere blink of an eye in cosmic terms. Their presence in Andromeda provides important data about the life cycles of massive stars, as they can help astronomers refine their models of how these stars change over time. Perhaps one of the strangest categories of stars in Andromeda are magnetars, neutron stars with incredibly powerful magnetic fields. These remnants of collapsed massive stars emit bursts of high-energy radiation and have magnetic fields trillions of times stronger than Earth's. The detection of magnetars in Andromeda suggests that the galaxy has experienced a significant number of supernova explosions, each of which could have left behind one of these highly magnetized remnants. The study of these objects helps scientists understand extreme physics in ways that cannot be replicated in laboratories on Earth. Variable white dwarfs are tiny but dense remnants of dead stars that sometimes show unexpected variations in brightness, which can be caused by pulsations or interactions with surrounding material. Unlike more common white dwarfs, these rare versions may be part of binary systems where they are slowly pulling material from a companion star. In some cases, this process can lead to a sudden thermonuclear explosion known as a nova, temporarily making the white dwarf thousands of times brighter before it fades back into obscurity. Each new observation adds to the growing understanding of how stars evolve, how galaxies change over time, and how different cosmic environments influence the life cycles of stars. These hidden luminaries, often overlooked in broader discussions of galaxies, provide essential clues about Andromeda's past and its future, showing that even within a well-studied galaxy, there are still mysteries waiting to be uncovered. Stellar congregations, overlooked star clusters. Andromeda is not just a collection of isolated stars, but a vast cosmic landscape where stars gather in clusters, forming communities that evolve together. Some of these clusters are dense and ancient, while others are loosely bound and relatively young. One of the most striking types of clusters found in Andromeda is the population of globular clusters. These dense, spherical groupings of stars are among the oldest structures in any galaxy, often containing stars that formed early in cosmic history. Andromeda has far more globular clusters than the Milky Way, with estimates suggesting over 500 of them orbiting the galaxy. Some of these clusters, however, appear different from those typically seen in other galaxies. A few contain stars that are significantly younger than expected, raising questions about how they formed. Others seem to have unusual motions, suggesting they may not have originally belonged to Andromeda, but were captured from smaller galaxies during past collisions. Astronomers have also identified a surprising number of extended clusters in Andromeda, groups of stars that are not as densely packed as traditional globular clusters, but still remain gravitationally bound. These clusters are unusual because they blur the line between star clusters and small galaxies. Unlike typical globular clusters, which are tightly bound and relatively spherical, extended clusters have more spread-out structures and lower overall densities. Some scientists believe these objects could represent a transitional phase between clusters and dwarf galaxies, offering a rare glimpse into how galactic structures evolve over time. A particularly mysterious type of star cluster in Andromeda is the so-called faint fuzzy cluster. These clusters were first identified in Andromeda's outer regions and appear to be distinct from both globular clusters and open clusters. They contain old stars, similar to globular clusters, but are more loosely structured, making them less likely to survive for billions of years without being disrupted by gravitational forces. Some theories suggest they might have originated in a long-ago merger between Andromeda and a smaller galaxy, leaving behind remnants that have slowly dispersed over time. Andromeda also hosts an unexpected number of young massive clusters. These contain bright, hot stars that are only a few million years old. The presence of these young clusters is surprising because many of them are found in regions where star formation was thought to have largely ceased. Some of these clusters are located far from Andromeda's main star-forming regions, leading to speculation that they may have been formed by tidal interactions or triggered by past collisions with satellite galaxies. There are star clusters that do not match the chemistry of the rest of the galaxy. Some of these contain stars with unusual metal ratios. A few clusters even appear to have compositions more similar to those found in dwarf galaxies, rather than in a large spiral galaxy like Andromeda. This suggests that Andromeda has been absorbing smaller galaxies over time, with their star clusters becoming part of its stellar population. Studying these clusters provides evidence of Andromeda's history of mergers and acquisitions, allowing astronomers to reconstruct past events that shaped the galaxy into what it is today. The distribution of star clusters also raises questions. Some clusters are found in places where they should have long since been disrupted by gravitational forces, while others form patterns that suggest they may have originated from larger structures. Certain clusters even appear to be arranged in streams or arcs, possibly remnants of past mergers. These patterns suggest that Andromeda's halo is still in the process of being shaped by ongoing interactions with smaller galaxies. Some of Andromeda's overlooked clusters are even more difficult to classify. A handful of clusters appear to contain extremely massive stars that should not have survived for billions of years. Others contain an unusual mix of stars, with some appearing much younger than expected. These anomalies have led to speculation that some clusters might be temporary, held together only loosely by gravity, and destined to eventually dissolve into Andromeda's general stellar population. Advanced telescopes have revealed additional star clusters hidden in the dense regions near Andromeda's core, where they were previously obscured by dust and bright stellar light. These central clusters may hold clues about the supermassive black hole at Andromeda's heart, possibly interacting with its powerful gravitational forces. Other discoveries include star clusters at extreme distances from the galaxy, raising questions about how far Andromeda's influence extends into intergalactic space. Black holes unveiled, the enigmatic cause of Andromeda. At the heart of Andromeda lies one of its most powerful features, a supermassive black hole. This immense object, hidden deep within the galaxy's core, influences everything around it, shaping the motion of stars, bending light, and consuming matter that strays too close. Scientists have long suspected that most large galaxies harbor such black holes at their centers. Observations reveal that Andromeda's supermassive black hole, called M31 star, is about 140 million times the mass of the Sun, making it significantly more massive than the Milky Way's central black hole, Sagittarius A star. The presence of such a massive object at Andromeda's core raises questions about how it formed and grew to its current size. Some theories suggest that as Andromeda was absorbing smaller galaxies over billions of years, each brought its own black hole. These black holes merged, creating a single larger one at the galaxy's center. Surrounding M31 star is a dense, compact cluster of stars, an unusual feature that sets it apart from other galactic centers. These stars move at incredible speeds, pulled by the immense gravitational force of the black hole. Observing these motions helped astronomers confirm the black hole's existence, as only such an extreme concentration of mass could account for the way these stars behave. Unlike some other galaxies, M31 star does not currently appear to be consuming large amounts of matter. Many black holes at the centers of galaxies form what is known as an active galactic nucleus, where gas and dust swirl around them, heating up and producing powerful radiation. Andromeda's black hole, however, is relatively quiet, emitting only small amounts of X-ray and radio waves. Scientists believe this may be a temporary phase. It is possible that in the past, the black hole was more active, pulling in material and releasing energy that could have shaped Andromeda's core. Future collisions with gas clouds or even entire star systems could awaken it again, turning it into a more active and energetic feature of the galaxy. Beyond the central black hole, Andromeda may also contain smaller, intermediate mass black holes scattered throughout its structure. These black holes, ranging from hundreds to thousands of times the mass of the Sun, are thought to form from collapsing massive stars or by merging smaller black holes. While supermassive black holes dominate galactic centers, intermediate black holes remain difficult to detect and are among the most elusive objects in astronomy. Some of these smaller black holes may reside in the dense star clusters orbiting Andromeda. There is growing evidence that certain globular clusters may harbor black holes at their centers, influencing the movement of surrounding stars. If confirmed, these intermediate black holes could help explain how supermassive black holes grow over time. Scientists have even suggested that some of Andromeda's clusters may contain multiple black holes, creating complex gravitational interactions that could eventually lead to the formation of a larger black hole through repeated mergers. Wandering black holes do not remain in fixed locations but drift through the galaxy. These black holes may have formed from past galactic collisions, ejected from their original positions by powerful gravitational forces. Some could be the remnants of smaller galaxies that Andromeda consumed in the past. Black holes are extremely difficult to detect unless they interact with nearby matter. However, their gravitational influence can sometimes be observed when they pass in front of a distant star, momentarily bending and magnifying its light in a process known as gravitational lensing. These objects, though invisible to the eye, exert powerful gravitational forces that can affect star formation, disrupt planetary systems, and even alter the paths of entire star clusters. If Andromeda contains a large number of these hidden black holes, they could play a significant role in its evolution. Gravitational wave detectors, which sense ripples in space-time caused by merging black holes, may also help identify hidden black holes within Andromeda. As technology improves, astronomers will be able to explore these enigmatic objects in greater detail, uncovering more about their origins and impact on the galaxy. Dark matter's whisper, the invisible backbone. Without dark matter, Andromeda, along with the Milky Way and countless other galaxies, would not exist in its current form. One of the first clues to dark matter's presence in Andromeda came from the way the galaxy rotates. If Andromeda consisted only of the stars, gas, and dust that astronomers can see, then the outer regions of the galaxy should be moving much more slowly than the inner parts. The simplest explanation is that Andromeda is surrounded by an enormous halo of unseen material, stretching far beyond the visible edge of the galaxy and outweighing all the stars and gas combined. The sheer amount of mass needed to explain Andromeda's motion suggests that dark matter makes up most of the galaxy's total mass. If the stars, planets, and gas clouds that make up Andromeda were all that existed, their combined gravity would not be enough to keep the galaxy bound together. The distribution of dark matter in Andromeda is not uniform. Some regions appear to have higher concentrations than others. Scientists have mapped dark matter through gravitational lensing. By studying the way light curves as it passes through different parts of Andromeda's halo, astronomers can piece together an image of this invisible material. These studies suggest that dark matter is not completely smooth, but instead has a clumpy structure, possibly shaped by interactions with smaller satellite galaxies or by the gravitational forces at play within Andromeda itself. The presence of dark matter also influences how Andromeda interacts with its neighbors. Andromeda is part of the Local Group, a collection of galaxies that includes the Milky Way and dozens of smaller galaxies. The gravitational pull of dark matter in Andromeda's halo extends far beyond its visible borders, affecting the motion of nearby galaxies. Some of these galaxies, like the dwarf satellites orbiting Andromeda, may be held in place by dark matter's gravity, preventing them from escaping into deeper space. Others may be slowly falling toward Andromeda, drawn in by its unseen mass. One of the bigger mysteries surrounding dark matter in Andromeda is what will happen when the galaxy collides with the Milky Way in a few billion years. The visible stars and gas clouds of both galaxies will interact in dramatic ways, forming new star clusters and altering their structures. But dark matter, which does not interact in the same way, will behave differently. Instead of colliding directly, the dark matter halos of the two galaxies will pass through one another, their immense gravity reshaping the resulting merged galaxy. If dark matter is made of weakly interacting particles, as many theories suggest, then its distribution after the collision could could offer clues about its properties. If, on the other hand, dark matter has some degree of interaction with itself, there may be unexpected patterns in the way the galaxies merge. Did dark matter form at the same time as the rest of the galaxy, or was it already present in the early universe, shaping the first galaxies long before stars began to shine? Some theories suggest that dark matter particles were created in the moments after the Big Bang, spreading throughout the universe and acting as the foundation upon which galaxies like Andromeda later formed. Others propose that dark matter could be linked to unknown forces or particles not yet discovered. Scientists hope that by mapping dark matter in greater detail and observing its effects on Andromeda's stars, they may one day unlock the mystery of this invisible but essential component of the universe. Mapping the giant. Innovations in galactic cartography. One of the biggest challenges in mapping Andromeda is its sheer size. Even though it is the closest major galaxy to the Milky Way, the entire structure does not fit neatly into the field of view of most telescopes. Observing the galaxy in full requires piecing together countless smaller images, a process that takes years of effort. The Hubble Space Telescope created one of the most detailed views of Andromeda by stitching together thousands of separate exposures, forming a mosaic that revealed millions of stars across a vast stretch of the galaxy. Mapping Andromeda involves more than just taking pictures. Scientists must also measure distances, analyze motion, and determine the composition of different regions. One key method used in galactic cartography is spectroscopy, which helps determine the chemical makeup, temperature, and movement of stars and gas clouds. This allows researchers to map not just the locations of stars, but also how they interact with one another and how the galaxy has changed over time. Motion mapping is another critical tool. Andromeda is not a static object. It rotates, shifts, and even pulls in smaller galaxies. To track this movement, astronomers use Doppler shifts, which measure how the wavelength of light changes as an object moves toward or away from us. By analyzing these shifts across different parts of Andromeda, scientists can create a detailed rotational map of the galaxy, showing how different regions spin at different speeds. Interstellar dust scatters and absorbs light, making it difficult to see some parts of the galaxy. Certain regions are almost completely hidden in visible light. To overcome this, astronomers use infrared telescopes, which can peer through dust clouds and reveal structures that would otherwise remain obscured. The Spitzer Space Telescope provided a new perspective on Andromeda by mapping its dust-rich regions, offering insight into where new stars are forming. Andromeda contains vast amounts of hydrogen gas, which emits a specific wavelength of radio waves that can be detected even in regions where visible light is blocked. By mapping these emissions, scientists can create a blueprint of Andromeda's gas distribution, showing where new stars are likely to form and how the galaxy is replenishing its stellar population. Advancements in computational modeling have also revolutionized galactic mapping. Instead of relying solely on direct observations, astronomers now use simulations to recreate Andromeda's structure. These models take into account everything from star distribution to dark matter influences and gravitational interactions with other galaxies. By comparing simulated versions of Andromeda with real observations, scientists can refine their understanding of how the galaxy formed and evolved. Its satellite galaxies are also carefully charted. Some, like M32 and M110, are easily visible, while others remain difficult to detect. Large-scale surveys have revealed an entire system of dwarf galaxies. Tracking them helps astronomers understand Andromeda's gravitational influence and provides insight into how large galaxies grow by absorbing smaller ones. One of the most ambitious mapping efforts is focused on Andromeda's impending collision with the Milky Way. Scientists are using detailed observations and motion studies to predict exactly how the two galaxies will interact when they begin merging in about 4.5 billion years. By charting the movement of stars and gas within Andromeda, astronomers have been able to create computer models that simulate how the galaxies will combine, forming a new, larger structure in the distant future. Many mysteries still remain. Some regions of the galaxy are still poorly understood, and new technologies will be needed to uncover their secrets. Future space telescopes like the upcoming Nancy Grace Roman Space Telescope are expected to provide even more detailed maps of Andromeda, allowing astronomers to study individual stars, identify hidden structures, and refine models. Satellite galaxies, Andromeda's cosmic companions. Surrounding Andromeda are dozens of smaller galaxies, each one orbiting and interacting with the giant spiral in complex ways. They range in size and shape, from compact elliptical dwarfs to irregularly shaped systems that appear to be in the process of being torn apart. Some are easy to spot, even with amateur telescopes. M32 and M110 are the two most prominent, located relatively close to Andromeda's bright central region. M32 is a compact elliptical galaxy with a dense concentration of stars, while M110 is slightly larger and more diffuse, with evidence of past interactions with its massive host. Both are thought to be remnants of larger galaxies that Andromeda stripped of gas and outer layers long ago. Beyond these bright companions, there are many fainter dwarf galaxies that orbit Andromeda at greater distances. Some, like NGC 147 and NGC 185, have structures that resemble small versions of elliptical galaxies, with little active star formation and an older population of stars. Others, like IC10, are still forming new stars, suggesting they have managed to hold onto their gas despite Andromeda's gravitational influence. Early models suggested that these satellite galaxies should be scattered randomly, orbiting in different directions with no clear pattern. However, observations in recent years have revealed something unexpected. Many of Andromeda's satellites appear to be arranged in a vast, thin plane rather than distributed evenly in space. This discovery challenges existing theories of galaxy formation, as it suggests that these satellites may have formed from a single event, rather than being independent objects captured over billions of years. Some astronomers believe that Andromeda's satellite system is part of a much bigger pattern, possibly linked to the Milky Way's own group of dwarf galaxies. The idea is that these small galaxies may not be isolated objects, but instead part of vast cosmic filaments, long strands of dark matter and gas that stretch between galaxy clusters. Some of these satellites are in the process of being consumed, their stars and gas stretched into long streams as they spiral inward. Observations have revealed enormous arcs of stars and gas extending away from Andromeda, thought to be remnants of past mergers. These streams provide direct evidence that Andromeda has grown by absorbing smaller galaxies, a process that is still ongoing. One of the clearest examples of this cannibalistic behavior is the discovery of the giant stellar stream, a massive ribbon of stars stretching over 100,000 light-years across space. This stream is believed to be the remains of a dwarf galaxy that ventured too close to Andromeda and was gradually torn apart by tidal forces. Its stars, once part of a smaller independent system, are now merging into Andromeda's halo, blending into the larger galaxy's population. These interactions are not one-sided. While Andromeda is the dominant force, its satellite galaxies can also have subtle effects on their host. Their combined gravitational pull can influence the shape of Andromeda's outer regions, causing its disk to warp slightly. Over long timescales, these interactions may even affect Andromeda's overall structure, contributing to its evolution into the future. Since these dwarf galaxies are small and faint, their motion is strongly influenced by the dark matter that surrounds them. By tracking their orbits, astronomers can infer how dark matter is distributed around Andromeda. Some of Andromeda's satellites appear to be almost entirely made of dark matter. These so-called dark galaxies contain very few stars and little visible gas, yet they still have enough mass to be detected through their gravitational influence. Their existence poses interesting questions about how galaxies form and whether there are many more of these nearly invisible objects hidden throughout the universe. Some will eventually merge with Andromeda, their stars becoming part of the larger galaxy. Others may be flung into deep space due to gravitational interactions. As Andromeda itself moves closer to the Milky Way, its satellite system will also be affected, potentially leading to new collisions and mergers in the distant future. Supernova remnants, echoes of explosive transformations. A supernova occurs when a massive star reaches the end of its life, either through the rapid collapse of a single giant star or the violent destruction of a white dwarf in a binary system. The explosion releases an enormous amount of energy, blasting heavy elements into space and triggering shockwaves that ripple through the surrounding regions. In Andromeda, these events have played a key role in enriching the galaxy with new elements, shaping nebulae, and even influencing the formation of new stars. One of the most well-documented supernova remnants in Andromeda is the remnant of SN 1885A, a supernova that was observed from Earth in 1885. Unlike many others that fade into obscurity, this remnant remains an important subject of study. It was a type Ia supernova, the result of a white dwarf in a binary system accumulating too much mass and undergoing a runaway thermonuclear explosion. What makes SN 1885 particularly intriguing is its location, very close to Andromeda's core. The explosion left behind traces of iron and other heavy elements, and even today, astronomers can detect its faint shadow when observing the region. This supernova helped confirm that Andromeda is not so different from the Milky Way in its ability to host these massive cosmic events. Beyond individual cases, Andromeda is home to a vast network of supernova remnants, many of which are only detectable through X-ray and radio observations. These remnants appear as glowing shells of expanding gas, still energized by the shock waves of the original explosion. Some are relatively young, just a few thousand years old, still visibly sculpting the space around them. Others are older, their initial structures now blending into the interstellar medium as their energy slowly dissipates. The shock waves they generate stir up surrounding gas clouds, compressing them and sometimes triggering the formation of new stars. Without these explosions recycling elements and distributing them across the galaxy, Andromeda and every other galaxy would look very different. The heavier elements necessary for rocky planets, life, and even the basic chemistry of the universe owe their existence to these powerful blasts. By mapping these remnants, astronomers can trace the distribution of older stellar populations, determining where past generations of massive stars once thrived. Many remnants are found in the spiral arms, where active star formation has been occurring for millions of years. Others, however, are detected in more unexpected places, hinting at past bursts of activity that may not have been obvious through other forms of observation. Some remnants in Andromeda stand out due to their unusually high energy output. These remnants, often associated with rapidly spinning neutron stars or pulsars, suggest that certain supernovae left behind more than just expanding gas clouds. Instead, they created dense, rapidly rotating stellar remnants that continue to emit radiation long after the initial explosion. These pulsars serve as cosmic beacons, helping astronomers probe the physics of extreme matter and the forces at play in Andromeda's evolution. The influence of these stellar explosions does not stop at the boundaries of the remnants themselves. The expanding shock waves mix with interstellar clouds, altering their chemical composition. They accelerate cosmic rays, high-energy particles that move through space at nearly the speed of light. These cosmic rays play a role in the heating and ionization of the gas within Andromeda, affecting the conditions under which new stars form. If certain supernova remnants appear in unexpected locations or with unusual properties, it may suggest that Andromeda has absorbed material from past mergers. Some of the most ancient remnants may not have originated within Andromeda itself, but instead come from dwarf galaxies that were consumed by its gravitational pull. Variable stars, pulses in the galactic heartbeat. Variable stars are among the most important tools in astronomy, acting as natural beacons that help astronomers measure distances, track stellar evolution, and understand the inner workings of galaxies. These stars do not shine with a steady light. Instead, they brighten and dim over time, sometimes in predictable cycles and sometimes in chaotic bursts. In Andromeda, thousands of variable stars have been identified, each offering a unique glimpse into the complex dynamics of the galaxy. One of the most well-known types of variable stars is the Cepheid variable. Even today, Cepheid variables remain one of the most reliable distance markers, helping astronomers refine measurements of Andromeda's vast scale. But they are not the only pulsating stars scattered throughout Andromeda. RR Lyrae stars, another class of variable stars, follow a similar pattern but are smaller and older. These stars are commonly found in the galaxy's dense halo and globular clusters, where ancient stellar populations reside. By studying their rhythmic pulses, astronomers can trace Andromeda's oldest structures, identifying regions that have remained largely unchanged for billions of years. Unlike Cepheids, which help measure distances to galaxies, R Lyrae stars serve as indicators of ancient stellar movements and past galactic interactions. There are also variable stars whose brightness shifts due to external factors rather than internal pulsations. Eclipsing binary stars are pairs of stars that orbit each other, periodically blocking each other's light from our view. When one star moves in front of the other, the total brightness of the system dips. By carefully analyzing these changes, astronomers can determine the sizes, masses, and orbits of the stars in these systems. Andromeda is home to countless eclipsing binaries, ranging from massive, short-lived blue giants to dim red dwarfs locked in slow, decades-long dances. Cataclysmic variables, such as nova systems, experience sudden outbursts when material from one star in a binary system falls onto the other. The sudden burst of light can make a once invisible star flare up dramatically before fading again. Long-period variables, such as mirror-type stars, change brightness over months or even years. These are often red giants nearing the end of their lives, pulsating as they lose mass and cool. These aging stars are responsible for seeding Andromeda's interstellar medium with carbon and other elements that will later be incorporated into new generations of stars and planets. By tracking these long-period variables, astronomers can study the later stages of stellar evolution in real time, watching as old stars transition into planetary nebulae or white dwarfs. In the central bulge, many of the variable stars belong to older populations. In the spiral arms, younger variable stars dominate, including Cepheids and other bright, short-lived stars that formed from recent waves of star formation. The halo, where globular clusters orbit far from the galactic center, hosts a mix of RR Lyrae stars and other old variables, tracing the movement of stars that may have once belonged to smaller galaxies that Andromeda absorbed. Unusual spiral structures, patterns and anomalies. At first glance, Andromeda appears to follow the classic design of a spiral galaxy, with well-defined arms curving outward from the bright central bulge. But some features do not match the expected symmetrical form seen in other galaxies, raising questions about its past and future evolution. One of the first unusual aspects of Andromeda's structure is the presence of two overlapping spiral patterns. Unlike the Milky Way, which has a clear dominant set of arms, Andromeda appears to have two distinct spirals that do not fully align. This strange, double structure is believed to be the result of a past collision, possibly with one of its satellite galaxies. Another anomaly is the uneven brightness and density of Andromeda's spiral arms. In most spiral galaxies, the arms form well-defined continuous structures, where stars, gas, and dust are concentrated. However, in Andromeda, the arms are somewhat fragmented, with varying densities across different regions. Some parts of the arms are packed with young, bright stars, while others appear more diffuse and less structured. This uneven distribution suggests that gravitational interactions, both past and present, continue to shape the galaxy's spiral form. Beyond the large-scale spiral arms, Andromeda has a series of smaller, faint structures that extend outward in unusual patterns. These faint arms and filaments are difficult to see with the naked eye, but become visible through deep sky imaging. Some of these structures appear to be tidal debris, remnants of past galactic mergers. Others may be the results of density waves, where the movement of stars and gas through the galactic disk creates temporary patterns that shift over time. Unlike the main spiral arms, which are relatively stable over millions of years, these smaller patterns can change more quickly. A particularly striking feature of Andromeda's spiral structure is the asymmetry in its inner disk. One side of the galaxy's core appears to have a more pronounced arm than the other, creating an imbalance. This lopsided structure is unusual for a galaxy of Andromeda's size, and suggests that an external force may have played a role in shaping it. One possible explanation is that Andromeda's disk is still settling from a past interaction with another galaxy. The gravitational influence of a passing or merging galaxy could have pulled stars and gas into an uneven arrangement, leaving behind a distorted spiral pattern. Some astronomers believe that dark matter could be responsible for some of Andromeda's spiral irregularities. As this invisible mass interacts with the normal matter in the galaxy, it may create disturbances that alter the formation and evolution of the spiral arms. In many spiral galaxies, star formation is concentrated along the leading edges of the arms, where gas and dust are compressed as they move through the galactic disk. In Andromeda, however, some regions of intense star formation are located outside the main spiral arms, forming scattered clusters of young, bright stars. This suggests that the spiral arms alone do not dictate where new stars will form. Other factors, such as the movement of interstellar clouds and shock waves from past collisions, may also play a significant role. Unlike the continuous curves of a traditional spiral galaxy, Andromeda has several circular patterns that resemble faint rings of stars and gas. Some of these rings are thought to be the results of past collisions, where the impact of a smaller galaxy created expanding waves that spread outward. These rings may slowly dissolve over time, blending into the surrounding spiral arms or evolving into new structures altogether. Beyond the visible spiral arms, the galaxy extends into a vast faint halo. This extended disk is not a smooth continuation of the inner spiral structure, but is instead made up of irregular shifting patterns. Some of these patterns may be remnants of ancient tidal interactions, while others could be shaped by Andromeda's ongoing gravitational relationship with its satellite galaxies. This outer region remains one of the least understood aspects of Andromeda's structure. Unlike the textbook images of perfect spiral galaxies, Andromeda reveals a more dynamic and complex reality, one where the forces of nature constantly reshape the fabric of a galaxy over billions of years. Beyond our solar system, the hunt for extragalactic planets. Finding planets outside our own solar system has been one of the most exciting developments in modern astronomy. For decades, scientists have searched for exoplanets, planets orbiting stars beyond the Sun, within the Milky Way. Thousands have been confirmed, and many more are waiting to be discovered. But the ultimate challenge lies in pushing the boundaries of detection even further, identifying planets in another galaxy. The Andromeda Galaxy, with its billions of stars, offers an immense frontier in this search. Exoplanet detection in the Milky Way relies on several well-established methods. The most successful is the transit method, which looks for tiny dips in a star's brightness when a planet crosses in front of it. Another key technique is the radial velocity method, which measures how a planet's gravity causes its host star to wobble slightly. These techniques work well for planets orbiting relatively close stars within our own galaxy, but they become increasingly difficult to use at greater distances. When looking toward Andromeda, the vast separation between us and its stars makes direct observation nearly impossible with current technology. Despite these challenges, astronomers are developing new ways to search for extragalactic planets. One promising approach involves gravitational microlensing. When a massive object, such as a star or even a planet, passes in front of a more distant star, it bends and magnifies the light from that background star. If a planet is present around the intervening star, its gravitational influence can create a secondary brightening, revealing its presence. Unlike the transit or radial velocity methods, microlensing does not require direct observation of the planet, or even the ability to resolve individual stars in a distant galaxy. In 2020, astronomers reported the possible detection of a planet in another galaxy using microlensing. The candidate planet, located in the Whirlpool galaxy, was identified through subtle distortions in X-ray emissions from a binary system. While this detection remains unconfirmed, it suggests that microlensing could be a viable tool for future discoveries. Applying this method to Andromeda is a natural next step. The galaxy's dense core, filled with overlapping stars, provides an ideal setting for microlensing events to occur. If observed consistently over time, Andromeda's background stars may reveal momentary brightening patterns that indicate planetary systems in action. Andromeda's sheer distance means that even if planets are detected, confirming their characteristics is a difficult task. Within the Milky Way, follow-up observations can refine estimates of a planet's size, composition, and atmosphere. But in another galaxy, the best scientists can currently hope for is indirect evidence of a planet's presence. Determining details such as whether a planet is rocky or gaseous, or whether it has a thick atmosphere, remains beyond our reach. Future space telescopes, equipped with more sensitive instruments, may one day provide breakthroughs in this area. Within our own galaxy, astronomers use the concept of the habitable zone, a region around a star where conditions might allow liquid water to exist. Many of the exoplanets detected so far orbit within these zones, raising the possibility that they could support life. But applying this concept to Andromeda is far more complicated. Even if a planet were found in the right orbit around a suitable star, confirming whether it has water, an atmosphere, or other key ingredients for life would be impossible without much more advanced technology. Given the similarities between Andromeda and the Milky Way, it is likely that many types of planetary systems mirror those found closer to home. There would be gas giants circling their stars at great distances, rocky planets locked in tight orbits, or frozen worlds in the outskirts of the galaxy. Some may resemble Earth, while others could be entirely unlike anything we have seen before. One of the most intriguing possibilities is the existence of planets in regions of Andromeda that have undergone significant stellar interactions. Unlike the Milky Way, which has had a relatively stable history, Andromeda has merged with and absorbed multiple smaller galaxies. These mergers can disrupt planetary systems, sending planets into new orbits or ejecting them into interstellar space. Some scientists suggest that Andromeda may be home to a large number of rogue planets, worlds that no longer orbit any star. These drifting planets could be abundant in the galaxy's outer halo, left behind by past gravitational disturbances. If planets do exist in Andromeda, their environments could be shaped by the unique conditions of their surroundings. In the core of the galaxy, planets orbiting stars in the central bulge would experience intense radiation, making habitability unlikely. In the spiral arms, conditions might be more stable, similar to those in the Milky Way. The presence of supernova remnants, star clusters, and even intermediate mass black holes in some regions of Andromeda could create environments where planetary formation is disrupted or altered. The growing field of artificial intelligence is also being applied to exoplanet research, with machine learning algorithms helping to identify subtle signals in astronomical data. These advances could eventually lead to the first confirmed detection of planets in Andromeda, opening a new era in the search for worlds beyond our galaxy. The feasibility of intergalactic travel. Intergalactic travel remains one of the most complex and speculative challenges in physics. The sheer scale of the distances involved makes even the fastest spacecraft ever built seem impossibly slow. Yet, despite these challenges, the idea of traveling beyond the Milky Way to reach distant galaxies like Andromeda continues to spark wonder. Scientists and engineers have, over the years, explored theoretical approaches and advanced technologies that could one day make such journeys feasible. The most immediate challenge is speed. Andromeda is located approximately 2.5 million light-years away. That means even a spacecraft traveling at the speed of light, something currently far beyond our capability, would take 2.5 million years to arrive. The fastest space probe ever built, NASA's Parker Solar Probe, moves at about 430,000 miles per hour. At that speed, a trip to Andromeda would take over 4,000 times longer than the entire history of human civilization. Clearly, if intergalactic travel is to become a reality, an entirely new form of propulsion is needed. In Einstein's theory of relativity, as an object approaches the speed of light, time slows down for those aboard. This means that while an intergalactic journey might take millions of years from an outside observer's perspective, the passengers could experience a much shorter trip. However, achieving such speeds is far beyond our current technology. Conventional rocket propulsion, which relies on chemical reactions, is completely insufficient. Scientists are looking towards more exotic propulsion methods, including nuclear fusion, antimatter, and even harnessing the power of space itself. A leading candidate is the light sail, propelled by powerful lasers. The Breakthrough Starshot initiative is already exploring this idea, with plans to send tiny probes to the nearby Alpha Centauri system using high-powered laser beams to accelerate them to 20% of the speed of light. Scaling up this technology for intergalactic travel would require an enormous energy source. But in theory, a large enough laser array could push a spacecraft to near-light speeds. Another approach is antimatter propulsion. Antimatter is the most energy-dense substance known, releasing immense amounts of energy when it interacts with regular matter. A spacecraft powered by controlled antimatter reactions could achieve speeds far beyond chemical rockets, though producing and storing enough antimatter is currently beyond our capabilities. Theoretically, if a spacecraft could reach speeds close to the speed of light, time dilation effects would allow travelers to experience the journey to Andromeda in just a few decades rather than millions of years. Some scientists have explored the idea of using black holes or other extreme astrophysical objects to assist in travel. A concept known as the Alcubierre warp drive, based on a solution to Einstein's field equations, suggests that space itself could be contracted in front of a spacecraft and expanded behind it, allowing for effective faster-than-light travel without violating relativity. This idea is highly theoretical and would require exotic forms of energy that have not yet been observed, such as negative mass. There is also the possibility of using naturally occurring cosmic shortcuts. Wormholes, if they exist, could theoretically connect distant points in space and time, creating a bridge that bypasses the vast distances between galaxies. However, no direct evidence of wormholes has been found, and even if they do exist, stabilizing one for safe passage would require unknown forms of exotic matter. Some physicists believe that if advanced civilizations exist, they may have already mastered such technologies. Beyond propulsion, the question of survival becomes critical. An intergalactic journey lasting thousands or even millions of years would require either a way to sustain life for extended periods or the ability to place travelers in suspended animation. Hibernation technology, inspired by the way some animals enter deep sleep states, is being researched for long-term space missions. Cryogenic freezing is another possibility, though the biological challenges of safely reviving a frozen human remain unsolved. An alternative to human travel is the use of self-replicating robotic probes. This idea, first proposed by mathematician John von Neumann, suggests that spacecraft equipped with advanced artificial intelligence and manufacturing capabilities could travel to distant galaxies, use local resources to build copies of themselves, and continue the journey indefinitely. Over time, such a system could spread throughout the universe, gathering and transmitting information without requiring human passengers. While today such ideas remain firmly in the realm of theory, the rapid advancement of technology means that concepts once thought impossible may one day become achievable. Navigating the cosmic void. Challenges of long-distance voyages. Traveling across vast cosmic distances presents an array of physical and engineering challenges that extend far beyond simply achieving high speeds. The enormity of space is not just a matter of distance, but of survival, precision, and endurance. For any spacecraft attempting to leave the Milky Way and navigate the intergalactic void toward Andromeda, it must overcome extreme environmental conditions, energy limitations, mechanical failures, and the vast stretches of emptiness that offer no opportunity for resupply or repair. One of the most immediate concerns is shielding a spacecraft and its crew from the hazards of deep space. Within the solar system, astronauts are protected to some degree by Earth's magnetic field and the Sun's heliosphere, which deflects a portion of harmful cosmic radiation. However, beyond this protective bubble, the galaxy is filled with high-energy cosmic rays, particles accelerated to nearly the speed of light by supernovae and black holes. Over long durations, exposure to such radiation would pose severe risks to human travelers, damaging DNA, increasing cancer risks, and slowly degrading electronic systems. Shielding against this requires either incredibly thick protective layers, which add significant mass to a spacecraft, or the development of active shielding methods that generate artificial magnetic fields. Even with adequate protection from radiation, intergalactic travelers would need to contend with the sheer emptiness of space. Unlike within a solar system, where planets, asteroids, and moons offer occasional opportunities for landing or resource gathering, the void between galaxies is largely empty. There are no way stations or natural refueling points. A spacecraft must carry everything needed for its journey from the start, which includes fuel, food, water, and spare parts. This introduces a serious engineering problem: how to store, preserve, and manage such resources for a journey that could take potentially millions of years. Current chemical rocket technology is completely inadequate due to its inefficiency. More advanced methods, such as nuclear propulsion or ion drives, offer greater fuel efficiency, but even they may not be enough to sustain a mission lasting thousands of years. One proposed solution is a spacecraft that continuously collects fuel as it moves. A Busar ramjet, for example, is a theoretical concept that would use immense electromagnetic fields to scoop up hydrogen from interstellar space, using it as fuel for a fusion reactor. While this idea has yet to be proven, it represents the kind of outside-the-box thinking required for long-distance space travel. Navigation presents another significant hurdle. Within the solar system, spacecraft rely on radio signals from Earth to determine their position, and planetary bodies provide clear reference points. However, in the vast, largely featureless void between galaxies, precise positioning becomes much more difficult. Stars become fainter, and the usual navigational markers disappear into the cosmic backdrop. A spacecraft traveling to Andromeda would need an autonomous navigation system capable of adjusting its course using whatever celestial landmarks are available. Pulsar-based navigation, which uses the steady signals from rapidly spinning neutron stars, has been suggested as one potential solution. In a journey lasting thousands of years, wear and tear would be inevitable. Micrometeoroids and interstellar dust, while sparse, could gradually erode the outer layers of a ship traveling at high speeds. Even tiny impacts could, over time, weaken protective shielding and threaten internal systems. Self-repairing materials or robotic maintenance units would likely be necessary to continuously monitor and fix any damage. If a spacecraft relies on spinning habitats for artificial gravity, the mechanical parts of these structures must endure relentless motion without failure. Communication over such vast distances presents another formidable challenge. At present, signals from Earth to even the most distant space probes, such as Voyager 1, take more than 22 hours to reach their destination. A spacecraft traveling toward Andromeda would soon find that communication delays become measured in years, then centuries, and eventually millennia. If an intergalactic vessel were to send a message back to Earth after 1,000 years of travel, the civilization that launched it may no longer exist by the time the signal arrived. This necessitates a level of self-sufficiency never before attempted in human exploration. The crew, whether human or artificial intelligence, would need to function entirely independently of Earth's support. Solar power, which is a reliable energy source within the solar system, becomes far less effective in the intergalactic void, where no nearby stars provide sufficient illumination. A spacecraft would need an alternative long-term power source, such as fusion-based energy systems. The challenge is not just generating power, but doing so in a sustainable way that does not rely on constant refueling. If human passengers are on board, maintaining life support systems for extended durations is an even greater concern. A closed-loop ecosystem, where oxygen, water, and nutrients are continuously recycled, would be necessary. Even the International Space Station, which relies heavily on supply shipments from Earth, struggles with maintaining perfect recycling efficiency. A deep space vessel would need an almost flawless system, capable of sustaining life for generations without external input. Hydroponic or aeroponic farming could provide food, but ensuring long-term biological stability remains an unsolved problem. The isolation of a multi-generational voyage could have profound effects on crew members. Unlike space missions within our solar system, where astronauts have the hope of returning home, intergalactic travelers would be leaving Earth permanently. They, or their descendants, would live their entire lives on a spacecraft, knowing that they would never see their destination. Social structures, governance, and cultural preservation over millennia must all be considered. Some of these challenges could be mitigated if the travelers were not human but robotic. Advanced artificial intelligence systems, designed to make independent decisions and repair themselves over long durations, could carry out such missions with fewer concerns about life support. However, even machines degrade over time, and software errors or mechanical failures could accumulate. Self-replicating machines, capable of repairing and even building new versions of themselves using available materials, may offer a solution. Simulating the future, Andromeda meets the Milky Way. The future of our galaxy is not a mystery. Scientists have turned to advanced simulations to predict what will happen when the Milky Way and Andromeda inevitably collide. This event, set to unfold over the next several billion years, will reshape both galaxies in ways that can already be modeled with surprising accuracy. Using powerful computers and decades of astronomical data, researchers have constructed detailed predictions of how this slow-motion cosmic dance will unfold, revealing a future that is both chaotic and fascinating. Andromeda is moving toward the Milky Way at a speed of about 110 kilometers per second. At this rate, the galaxies will begin their first close encounter in roughly 4.5 billion years. Unlike the high-speed collisions of asteroids or spacecraft, this is not a sudden crash. The enormous size and vast distances between stars mean that individual stars are unlikely to collide directly. Instead, the gravitational forces between the two galaxies will distort their shapes, stretching and pulling them into long tidal streams. These tidal effects will create sweeping arcs of stars and gas, twisting both galaxies into chaotic forms before they eventually merge into a single, larger structure. Astronomers input data about the mass, velocity, and composition of each galaxy, allowing computers to calculate how gravity will shape their interactions. By running multiple simulations with slightly different initial conditions, scientists can predict a range of possible outcomes. The general consensus, however, is that Andromeda and the Milky Way will undergo a long and complex merger, with each galaxy passing through the other multiple times before fully combining. The first encounter will be the most dramatic. As the galaxies approach, their mutual gravitational pull will distort their spiral arms, sending vast streams of stars and gas out into intergalactic space. Andromeda's massive core will likely pass through the Milky Way, pulling material with it and triggering bursts of new star formation. The compression of gas clouds will ignite a wave of stellar birth, lighting up the merging galaxies with newly formed stars. Some of these stars will form massive clusters, while others may eventually collapse into black holes, adding to the growing number of these mysterious objects within the new galaxy. As the galaxies continue their interactions, they will experience repeated close passes. With each encounter, gravitational forces will strip away more of their original structures. The familiar spiral arms of both galaxies will become increasingly disrupted, stretched, and distorted into elongated tidal tails. Some stars may be flung out entirely, cast into intergalactic space, where they will drift alone for billions of years. Others will settle into new orbits as the two galaxies gradually merge their stellar populations. After several billion years of these interactions, the galaxies will finally settle into a single, stable shape. Simulations suggest that the end result will not be a spiral galaxy like Andromeda or the Milky Way, but rather a giant elliptical galaxy. This transformation occurs because the violent merger process randomizes the orbits of stars, erasing the organized disk structure characteristic of spiral galaxies. Instead of rotating in an orderly fashion around a central disk, the stars will move in a more chaotic, three-dimensional pattern, giving the newly formed galaxy an elliptical shape. As an elliptical galaxy, it will have a different structure and behavior than the spirals that formed it. The random stellar motions that characterize elliptical galaxies will mean that over time, stars will mix more thoroughly than in a well-ordered spiral system. Without the continuous rotation that maintains spiral arms, the merged galaxy will evolve into a more uniform, rounded shape. Its color will shift as well, where the Milky Way and Andromeda once contained vibrant blue star-forming regions. The newly merged system will gradually take on a more golden hue. This change reflects the aging population of stars as the brightest and hottest stars burn out, leaving behind longer-lived but cooler reddish stars. Scientists have even given this future galaxy a name, Milkomeda. While it will retain many features of its parent galaxies, it will also be much larger, and the central region will likely host an even more massive black hole, as the supermassive black holes from both galaxies will eventually spiral toward each other and merge. By the time the merger begins, Earth's solar system will be billions of years older, and the Sun will have significantly evolved. In about 5 billion years, the Sun is expected to expand into a red giant, making life on Earth impossible. However, if humanity, or any other intelligent species, has managed to survive and expand into space, the galactic merger could provide new opportunities. The influx of gas from Andromeda would fuel star formation, creating new potentially habitable worlds. The redistribution of stars and planets would alter cosmic environments, changing the structure of interstellar space and perhaps even providing easier routes for intergalactic travel. The sheer distances between stars mean that direct star-to-star collisions are highly unlikely. Instead, the primary effects will be gravitational, influencing the motion of stars and reshaping the large-scale structure of the galaxy. Some planetary systems could be thrown into new orbits, while others might be ejected entirely. There is even a small possibility that our solar system could be displaced from its current location, moving deeper into the new galaxy, or being flung outward into intergalactic space. Some simulations suggest that after the merger is complete, Milkomeda will settle into a quiet period, with most of its chaotic interactions calming down. Others propose that Milkomeda may go on to merge with other nearby galaxies, continuing the process of galactic evolution on an even larger scale. As the universe continues to expand, the connections between galaxies will become weaker. The distant galaxies that are visible today will move farther and farther away, their light redshifting into the background of an ever-expanding cosmos. In the far future, only the closest galaxies, those that have already merged or are bound together by gravity, will remain within observational reach. This means that long after the collision, Milkomeda will stand as an island in an increasingly empty universe, one of the few remaining large galaxies in an ever-darkening sky. The universe is filled with examples of galactic collisions at various stages, from early encounters to fully merged elliptical galaxies. By observing other galaxies currently in the process of merging, astronomers can compare real-world data with their simulations, refining their models and improving their understanding of the forces at play. While humans will not witness this event firsthand, our ability to predict and simulate the future allows us to glimpse a time when the night sky will be radically different. Comparative anatomy: Andromeda versus the Milky Way. Both galaxies belong to the Local Group, a collection of more than 50 galaxies dominated by these two massive spirals. They each have billions of stars, expansive arms stretching across space, and supermassive black holes at their centers. Yet, their individual histories and structures reveal variations that shape their present and future. Andromeda is larger in terms of visible diameter, spanning roughly 220,000 light-years across, compared to the Milky Way's estimated 100,000 to 160,000 light-years. However, the Milky Way may be slightly more massive, due to its dense core and extended halo of dark matter. These differences raise questions about how galaxies grow over time and what factors contribute to their overall mass. Andromeda's expansive disk suggests that it has consumed more small galaxies over time, accumulating stars and material to extend its reach. Andromeda is estimated to contain about 1 trillion stars, more than double the number in the Milky Way, which has around 200 to 400 billion. This difference suggests that Andromeda has been more efficient in forming stars, or has merged with enough smaller galaxies to boost its stellar population. However, the overall rate of star formation tells a different story. Andromeda's star formation has slowed considerably, whereas the Milky Way remains relatively active in producing new stars. The presence of bright blue clusters and nebulae in the Milky Way's spiral arms points to an ongoing cycle of stellar birth, while Andromeda appears to be entering a quieter phase. Andromeda's central bulge is larger and more prominent than the Milky Way's, housing older, redder stars in a dense configuration. This suggests a history of major interactions and mergers that funneled material into the core, sparking starbursts in the past. The Milky Way's central region, though also densely packed, is not as pronounced, indicating a less violent past or a different pattern of stellar migration over billions of years. The black hole at the center of Andromeda, M31 star, has an estimated mass of about 140 million times that of the Sun. In contrast, the Milky Way's Sagittarius A star is around 4 million times the Sun's mass. The difference in size suggests that Andromeda's central region has undergone more dramatic processes, possibly including the accretion of multiple smaller black holes over time. The presence of a larger black hole also influences the motion of nearby stars, creating a more dynamic and energetic environment near Andromeda's core. Both galaxies spin, with their spiral arms sweeping through space in a grand cosmic motion. However, Andromeda's rotation is faster, with its stars moving at an average speed of about 250 kilometers per second. The Milky Way stars, by comparison, travel at approximately 220 kilometers per second. This difference may be due to variations in mass distribution, with Andromeda's larger stellar population and central bulge contributing to its higher rotational velocity. Despite these differences, both galaxies share fundamental structural features. Each has a barred spiral shape, meaning that their central regions contain elongated bars of stars that channel material inward, fueling star formation and feeding their central black holes. These bars are common among spiral galaxies and are thought to develop as a result of gravitational interactions over time. Their satellite galaxies also show similarities and differences. Both galaxies are surrounded by a collection of smaller companions, including dwarf galaxies and globular clusters. The Milky Way has known satellites such as the Large and Small Magellanic Clouds, as well as the Sagittarius dwarf galaxy, which is currently being torn apart by gravitational forces. Andromeda's system includes satellites like M32 and M110, which show signs of past interactions with their parent galaxy. Recent studies suggest that Andromeda's satellites are arranged in a surprisingly ordered plane, whereas the Milky Way's are more randomly distributed, hinting at different formation histories. Infrared revelations. Seeing Andromeda in a new light Much of Andromeda's true complexity is hidden behind thick clouds of dust that absorb and scatter visible light. This dust acts like a cosmic curtain, obscuring large portions of the galaxy and making it difficult to see the full picture. Infrared light, however, is capable of passing through these obstacles. By observing Andromeda in infrared wavelengths, astronomers can reveal structures and processes that remain invisible to traditional optical telescopes. One of the most striking discoveries made through infrared observations is the detailed structure of Andromeda's dust lanes. In visible light, these lanes appear as dark streaks weaving through the spiral arms, blocking the light of stars behind them. But in infrared, these same structures glow, revealing intricate networks of dust that trace the skeleton of the galaxy. This dust is a crucial ingredient for star formation. Infrared images expose vast reservoirs of cold gas and dust that serve as the raw material for new stars. By studying these regions, astronomers can pinpoint where the next generation of stars will be born, long before they become visible in optical wavelengths. The heart of the galaxy is densely packed with stars, and in visible light, their combined brightness creates a blinding glow. This makes it difficult to study individual stars or structures near the core. Infrared telescopes can cut through the glare, revealing the finer details of Andromeda's nucleus. Surrounding the central supermassive black hole is a dense, rotating disk of stars. In visible light, this region appears as a bright, featureless core. But in infrared, astronomers can distinguish the complex motions of stars as they orbit under the influence of the black hole's immense gravity. As stars age, they undergo changes that make them more prominent in infrared wavelengths. Red giant stars, in particular, emit much of their light in the infrared spectrum. By mapping the distribution of these stars, astronomers can trace the long-term history of the galaxy. When galaxies collide or interact, they often leave behind faint streams of stars, dust, and gas. These tidal tails and stellar streams can be difficult to detect in visible light, especially if they are spread out over vast distances. Infrared surveys, however, can pick up the warm glow of dust and faint stellar remnants left behind by these past encounters. Another key advantage of infrared observations is the ability to detect low-mass objects that are too faint to be seen in optical wavelengths. Brown dwarfs, sometimes referred to as failed stars, are objects that are too small to sustain nuclear fusion in their cores. These objects emit most of their radiation in the infrared spectrum, making them nearly invisible to regular telescopes. Infrared studies have revealed populations of brown dwarfs scattered throughout Andromeda, providing insight into the lower end of the galaxy's stellar population. These discoveries help fill in the gaps in our understanding of how stars and substellar objects form within a large galaxy. Radio whispers, unconventional views of Andromeda. While visible and infrared light reveal stars, dust, and heat, radio waves capture a different kind of picture, one shaped by magnetic fields, cold gas clouds, and the faint whispers of cosmic events that have unfolded over millions of years. One of the most important uses of radio astronomy in studying Andromeda is mapping its neutral hydrogen. Hydrogen in its neutral form emits a faint signal at a wavelength of 21 centimeters. This signal, known as the hydrogen line, allows astronomers to trace the distribution of gas throughout Andromeda. By tuning their instruments to this wavelength, researchers can construct detailed maps of the galaxy's gaseous structure, revealing where new stars may form and how Andromeda's spiral arms continue to evolve. Observations of hydrogen have revealed that Andromeda's disk extends much farther than it appears in optical images. While the bright part of the galaxy spans about 220,000 light-years, radio maps show that its gas extends even farther, blending into the surrounding intergalactic medium. Unlike visible light, which primarily reveals the physical structure of stars and dust, radio signals can be affected by the presence of magnetic forces. As charged particles spiral around magnetic field lines, they produce synchrotron radiation, a faint but steady emission that can be detected by radio telescopes. By mapping this radiation, astronomers have found that Andromeda has an organized magnetic field that stretches across much of the galaxy. This field helps guide the movement of cosmic rays and plays a role in shaping interstellar gas, influencing where and how stars form. Another discovery made with radio astronomy is the presence of pulsars within Andromeda. As pulsars spin, their beams sweep across space, creating rhythmic pulses that can be detected from Earth. Although Andromeda is millions of light-years away, sensitive radio telescopes have identified several pulsars within the galaxy, providing new insights into the end stages of stellar evolution in a system beyond our own. Andromeda's central region is also a source of intriguing radio emissions. M31 star, while not as active as the supermassive black holes found in some other galaxies, still emits a faint radio glow. This radiation comes from charged particles spiraling around the intense magnetic fields near the black hole. Radio waves allow astronomers to peer directly into this turbulent region. By studying these emissions, researchers can learn more about the feeding habits of the black hole and how it interacts with the surrounding environment. Beyond the central black hole, Andromeda also contains mysterious sources of radio waves that do not have clear counterparts in optical or infrared images. Some of these sources may be remnants of ancient supernova explosions where expanding shock waves have energized surrounding material, causing it to emit in radio wavelengths. Others may be regions of intense star formation, where young, massive stars are ionizing the surrounding gas and triggering bursts of radio emission. Identifying and understanding these sources remains an ongoing challenge, requiring continued observations with ever more sensitive instruments. Radio astronomy has also been instrumental in searching for signals that might hint at intelligent life. While there is no evidence so far, some astronomers have pointed radio telescopes toward Andromeda in the hopes of detecting artificial signals, structured patterns that differ from the random noise of natural cosmic processes. These searches, conducted as part of the broader effort in the Search for Extraterrestrial Intelligence or SETI, rely on the assumption that if intelligent civilizations exist in Andromeda, they might use radio waves for communication, just as humans do. The upcoming Square Kilometre Array telescope will have the ability to map the galaxy's magnetic field in even greater detail, detect fainter hydrogen signals, and uncover new sources of radio waves that have so far remained undetected. Through radio astronomy, Andromeda whispers its secrets across the vastness of space, offering clues to astronomers who are willing to listen. Gravitational lensing, Andromeda as a cosmic lens. One of the most valuable aspects of gravitational lensing is its ability to reveal hidden galaxies that existed in the early universe. Because Andromeda magnifies the light from distant objects, astronomers can use it as a kind of natural telescope, looking billions of years into the past. These magnified galaxies, seen as they were when the universe was much younger, provide crucial information about how the first stars and galaxies formed. Without Andromeda's gravitational influence, these distant cosmic structures would be nearly impossible to detect with even the most powerful telescopes. One of the challenges in detecting gravitational lensing in Andromeda is the presence of its own stars, gas, and dust. Because the galaxy is relatively close to Earth, its bright features can make it difficult to isolate the much fainter background galaxies being lensed. However, astronomers have developed sophisticated techniques to filter out the foreground noise, allowing them to focus on the gravitational distortions caused by Andromeda's mass. These methods involve carefully analyzing how light is stretched and amplified across different regions of the galaxy, revealing patterns that indicate the presence of lensing effects. Beyond studying distant galaxies, gravitational lensing can also be used to detect objects much closer to home. In rare cases, individual stars within Andromeda can act as tiny lenses, magnifying the light of even more distant stars in the background. This microlensing occurs when a star's gravity temporarily bends and brightens the light from another star directly behind it. These brief flashes of magnification can provide crucial insights into the distribution of unseen objects, including rogue planets, black holes, and even dark matter clumps drifting through the galaxy. Microlensing has already been used to detect planets beyond our solar system, and astronomers hope that applying the same technique in Andromeda may one day reveal extragalactic planets orbiting stars in a distant galaxy. Though challenging, such a discovery would mark a significant milestone in the search for planets beyond the Milky Way. The ability to detect planetary systems in Andromeda through gravitational lensing would offer a completely new way to study how planets form and evolve in different galactic environments. Scientists are also investigating the possibility that Andromeda's gravitational lensing could help test fundamental aspects of physics. Light traveling through a gravitational field does not just bend. It also experiences time delays. When multiple images of a background galaxy or quasar appear due to lensing, the light from each image takes a slightly different path through space. If the background source is variable, such as a flickering quasar, astronomers can measure the slight differences in arrival times between each lensed image. This time delay can provide valuable clues about the expansion rate of the universe and even help refine measurements of the Hubble constant, the number that describes how fast the universe is growing. Cosmic gateways, theoretical wormholes, and intergalactic shortcuts. The idea of wormholes originates from Einstein's theory of general relativity. The equations suggest that spacetime can be curved and warped by massive objects, and in some scenarios it could be bent in such a way that two distant points become directly connected by a hidden passage. This passage, often called an Einstein-Rosen bridge, would function like a tunnel through space, allowing for instantaneous travel between its two ends. If a stable wormhole existed between the Milky Way and Andromeda, it would remove the need for conventional propulsion, enabling near-instantaneous transit between the two galaxies. According to general relativity, a wormhole would naturally collapse almost as soon as it formed. To counteract this, scientists speculate that an exotic form of matter with negative energy, something not yet discovered, would be needed to hold the tunnel open. This exotic matter would push outward against the walls of the wormhole, preventing them from collapsing and allowing passage through. The search for wormholes has primarily been conducted through indirect means. Some researchers have proposed looking for their gravitational effects, similar to the way black holes can be detected. If a wormhole existed, light passing near it might be distorted in a way that differs from a normal gravitational lens. Some have even suggested that certain black holes might actually be entrances to wormholes, though this remains purely speculative. Observations of Sagittarius A star have not revealed any evidence of such a structure, but the search continues. Beyond the question of whether wormholes exist is another problem: how they would be navigated. If a wormhole connected the Milky Way and Andromeda, it would still require an entry point. Theoretically, a spaceship approaching a stable wormhole would experience extreme gravitational forces at its mouth. If the entrance was surrounded by high-energy radiation or an event horizon, reaching it could be impossible. Even if a ship could cross the threshold, the tunnel itself might not be smooth or direct. Some models suggest that a traveler could be stretched or compressed unpredictably inside the wormhole, making safe passage unlikely. Another challenge involves the potential effects of time dilation. In Einstein's relativity, the flow of time can change based on speed and gravity. If a wormhole connected two distant points in space, it might also connect two different moments in time. This raises complex questions about causality and paradoxes. In some scenarios, traveling through a wormhole could allow a person to arrive before they left, creating contradictions that physics has yet to fully resolve. If wormholes could be used in this way, they might not only serve as cosmic highways, but also as potential time machines, adding another layer of mystery to their theoretical existence. Other concepts have also been proposed that might offer similar shortcuts across the universe. One idea involves cosmic strings, extremely thin, high-energy structures that may have formed in the early universe. Some theories suggest that if two cosmic strings moved past each other at high speeds, they could warp space-time in a way that allows for shortcuts between distant locations. These structures, if they exist, could provide an alternative to the traditional wormhole model by creating natural paths through space. Some have explored the idea that tiny wormholes could exist at the quantum scale, constantly appearing and disappearing as part of space-time's underlying structure. If this is true, some speculate that an advanced civilization might one day learn how to stabilize and enlarge these quantum wormholes, creating usable passages between galaxies. This remains far beyond current technological understanding, but it highlights the possibilities hidden within the fabric of space itself. If a civilization could harness enormous amounts of energy, on a scale far beyond anything currently possible, it might be able to manipulate space-time directly. Theoretical models suggest that if negative energy could be generated and controlled, an artificial wormhole could be constructed and stabilized. If shortcuts through space-time exist, could the cosmos be interconnected in ways we do not yet understand? Some theories suggest that our universe might be part of a vast network of space-time tunnels, with galaxies and even entire universes linked by hidden pathways. Despite the uncertainties surrounding wormholes, their study remains an important part of theoretical physics. Even if they are never found or created, the pursuit of understanding them has over the years led to deeper insights into gravity, space-time, and the nature of the universe. Extragalactic habitability in Andromeda. The fundamental requirements for life as we know it remain the same, regardless of location. A planet must have a stable orbit around its star, be positioned within the habitable zone where liquid water can exist, and maintain an atmosphere capable of supporting complex chemistry. These factors are relatively well understood when studying exoplanets within the Milky Way. But when applied to Andromeda, they introduce new layers of complexity. The sheer distance to the galaxy makes it nearly impossible to directly study individual planets. However, by analyzing Andromeda's structure, stellar populations, and planetary formation theories, researchers can make educated guesses about where life might have the best chance to develop. One of the first indicators of potential habitability is the distribution of metal-rich stars. Planets capable of supporting life require elements heavier than hydrogen and helium, such as carbon, oxygen, and nitrogen, to form atmospheres and biological molecules. These elements are created within stars and distributed through supernova explosions. Andromeda has a well-mixed population of young and older stars. The younger stars suggest an ongoing process of planet formation, much like in the Milky Way, increasing the likelihood that rocky planets exist within habitable zones. Andromeda's history of mergers and interactions with smaller galaxies has shaped its current structure. Such galactic collisions can disrupt planetary systems by altering star orbits, triggering intense radiation bursts, or even ejecting planets into interstellar space. While Andromeda has largely settled from its past interactions, regions near its galactic core, or areas with high stellar density, may be too chaotic to support stable planetary systems over billions of years. The outer spiral arms, on the other hand, may provide more stable environments where planets could remain in predictable orbits long enough for life to develop. In our own galaxy, water-bearing exoplanets have been identified, along with icy moons that could harbor subsurface oceans. The icy moons show that life might not be limited to planets within the habitable zone of their stars. Instead, it could emerge on moons orbiting gas giants, protected beneath thick ice layers, where internal heating prevents water from freezing solid. The challenge is that detecting water in Andromeda's planetary systems is significantly harder than within the Milky Way. At Andromeda's distance, resolving individual stars at such a level of detail is currently beyond technological capabilities. Some scientists have speculated about the possibility of silicon-based life, which could thrive in environments that would be toxic to Earth-like organisms. Andromeda contains a variety of star types, from red dwarfs to massive blue giants, and the planets orbiting these stars may have a wide range of extreme conditions. Planets with thick atmospheres composed of ammonia or methane could host entirely different biochemistries, expanding the potential for habitability beyond what is considered typical for Earth-like life. In the Milky Way, astronomers look for biosignatures, chemical markers that suggest the presence of life, such as oxygen, methane, and carbon dioxide in exoplanet atmospheres. The detection of these gases in Andromeda would be significantly more difficult due to the limitations of current telescopes. However, future scientists could analyze the atmospheres of distant exoplanets, searching for the telltale signs of biological activity. Some researchers propose looking for planetary atmospheres that appear out of balance, where the presence of gases like oxygen and methane suggests active biological processes. The discovery of a planet with an unusual atmospheric composition could hint at life, even if the details remain unknown. If an advanced civilization existed in the galaxy, it might leave detectable signs through technology. Some astronomers have suggested searching for artificial signals, similar to the SETI efforts within our own galaxy. A sufficiently advanced civilization might use radio waves, laser pulses, or even energy-harnessing megastructures, such as Dyson spheres, to collect and utilize stellar energy. If such structures existed in Andromeda, they might produce infrared signatures detectable with sensitive instruments. However, the search for extraterrestrial intelligence faces many obstacles, including the sheer scale of Andromeda and the unknown variables involved in predicting alien technology. Civilizations could use communication methods entirely different from anything humans recognize, making their detection even more elusive. The age of Andromeda also presents an interesting consideration. It has been forming stars for billions of years, meaning that, if intelligent life arose early in its history, it could be significantly more advanced than humanity. Or, it might have already disappeared. The Andromeda Protocol, a blueprint for future space colonization. If humanity ever sets its sights on colonizing the Andromeda Galaxy, the effort would require a carefully structured and methodical approach. A mission of such scale would be unprecedented, demanding advanced technology, long-term planning, and a deep understanding of interstellar survival. The Andromeda Protocol, a theoretical blueprint for humanity's expansion beyond the Milky Way, would serve as a guiding framework for such a venture. It would outline the necessary stages of development, from the first exploratory missions to the establishment of self-sustaining colonies in another galaxy. The first step in any serious attempt to reach Andromeda would be the development of intergalactic propulsion systems capable of traversing the vast distances between galaxies. Achieving practical intergalactic travel would likely require breakthroughs in propulsion technology, such as antimatter engines or concepts like the Alcubierre warp drive. Before any large-scale human presence in Andromeda, the first phase of the protocol would likely involve sending robotic probes. These automated explorers would be designed to gather crucial data about Andromeda's planetary systems, star clusters, and potential hazards. Unlike current probes, which rely on radio signals that take minutes or hours to reach Earth, intergalactic probes would need advanced artificial intelligence capable of autonomous decision-making. They would identify habitable worlds, map the distribution of resources, and relay information back to the Milky Way through advanced communication systems, potentially using quantum entanglement or other speculative methods. Once a suitable target within Andromeda is identified, the next phase would involve sending self-replicating robotic factories to establish infrastructure before humans arrive. These systems, equipped with nanotechnology and 3D printing capabilities, could extract materials from asteroids or planetary surfaces, building essential structures such as space stations, habitats, and energy collection arrays. Automated terraforming efforts might begin on selected planets, altering their atmospheres to make them more suitable for human life. The use of bioengineered organisms, such as microbes capable of producing oxygen, could play a role in shaping planetary environments long before the first colonists set foot on alien soil. The method of transporting human settlers to Andromeda would be one of the most complex challenges in the protocol. The journey could take an unfathomable number of years, unless faster-than-light travel is developed, requiring multi-generational spacefaring civilizations to exist aboard colossal starships. These vessels, sometimes called world ships, would be self-sustaining, carrying entire ecosystems, manufacturing centers, and living quarters for populations that might never set foot on a planetary surface. Generational crews would live and die aboard these ships, preserving knowledge and adapting to an existence untethered from Earth. If human hibernation becomes viable, passengers could remain in a deep unconscious state for centuries, awakening only upon arrival in Andromeda. Alternatively, mind uploading, where human consciousness is transferred into artificial systems, could enable settlers to be transported digitally, stored within advanced AI networks, and later given physical form through robotic bodies or bioengineered clones upon reaching their destination. Upon arrival in Andromeda, establishing a foothold would require strategic planning. The first human outposts might begin as orbital habitats, large space stations positioned near resource-rich planetary systems. These stations would serve as operational hubs overseeing planetary exploration and surface landings. They would also act as waypoints for future arrivals, creating a network of interconnected settlements across Andromeda. Terraforming efforts could continue in parallel, ensuring long-term habitability for future generations. One of the most critical elements of the Andromeda Protocol would be the development of self-sustaining ecosystems. Unlike Earth, which has evolved its biosphere over billions of years, a new colony would need to construct its own life-supporting environment from scratch. Genetically engineered food sources and artificial biospheres could provide sustenance in environments where natural agriculture is impossible. A settlement in Andromeda would be isolated from Earth for thousands of years, if not permanently, making real-time communication impossible. The formation of independent societies, shaped by their specific environments and technological capabilities, could lead to entirely new cultural and political systems unlike anything on Earth. If Andromeda hosts intelligent civilizations, any human expansion would need to address the ethical and practical implications of contact. The Andromeda Protocol would likely include guidelines for first contact scenarios, ensuring that interactions are handled with caution and respect. If another civilization has already claimed parts of Andromeda as its domain, humanity might need to negotiate coexistence or risk conflict on an intergalactic scale. Defensive strategies would also need to be developed, both against natural cosmic hazards and potential hostile entities. Asteroids, gamma-ray bursts, and rogue black holes pose threats to any settlement, requiring constant monitoring and rapid response capabilities. If Andromeda is home to advanced extraterrestrial civilizations, humanity's expansion efforts would need careful diplomatic and strategic planning to avoid unintended aggression or territorial disputes. Despite the challenges, the colonization of Andromeda would represent a monumental step in the evolution of humanity. It would transform us from a species bound to one galaxy into an intergalactic civilization, capable of thriving across cosmic distances. Such a journey would not only test the limits of human ingenuity and endurance, but would also redefine the nature of life itself, bridging the gap between what is possible and what lies beyond imagination. Technological frontiers, new tools for extragalactic astronomy. One of the most important developments in modern astronomy is the improvement of large optical telescopes. These telescopes collect light from distant objects, forming detailed images of galaxies like Andromeda. The latest generation of ground-based telescopes, such as the Extremely Large Telescope, or ELT in Chile, is designed to capture images with unprecedented clarity. With a mirror more than 30 meters across, the ELT will be able to detect faint objects with greater precision than ever before. Adaptive optics, a technology that corrects for distortions caused by Earth's atmosphere, further enhances these images. By constantly adjusting mirrors to compensate for atmospheric turbulence, telescopes can now produce images almost as sharp as those taken from space. Space-based telescopes provide an even clearer view, free from the interference of Earth's atmosphere. The Hubble Space Telescope has been instrumental in studying Andromeda, capturing breathtaking images that reveal its structure in remarkable detail. More recently, the James Webb Space Telescope, or JWST, has taken this capability even further. Designed to observe in infrared light, JWST can peer through cosmic dust, revealing stars and planetary systems that were previously hidden. By analyzing infrared emissions, astronomers can study cooler objects, such as distant planets, star-forming regions, and ancient galaxies. In the case of Andromeda, JWST has provided new insights into its stellar populations and the movement of gas within the galaxy. The Square Kilometre Array, an upcoming network of radio telescopes, will be one of the most powerful tools for studying extragalactic structures. It will help scientists track how Andromeda's stars and interstellar material move over time. Unlike optical telescopes, radio observatories can operate even in cloudy conditions or during the day, providing continuous monitoring of astronomical phenomena. Spectroscopic instruments break down light into its component wavelengths, much like a prism creating a rainbow. This technique allows astronomers to determine the chemical composition, temperature, and motion of stars and gas clouds within a galaxy. The Keck Observatory, for example, uses advanced spectrographs to analyze the light from Andromeda's core, measuring the speed of its stars and revealing the presence of its central black hole. Spectroscopy has also been critical in identifying different generations of stars, showing how Andromeda's stellar population has evolved over time. The Gaia Space Observatory, operated by the European Space Agency, has revolutionized the study of our own galaxy by precisely measuring the positions and motions of over 1 billion stars. A similar approach is now being applied to Andromeda, allowing scientists to build a dynamic model of its structure. By tracking the movement of individual stars, researchers can reconstruct past interactions, detect streams of stars from absorbed galaxies, and predict how Andromeda will continue to evolve. Large surveys, such as those conducted by the Vera C. Rubin Observatory, generate images of millions of galaxies, requiring advanced software to analyze patterns and detect faint structures. AI algorithms can quickly identify anomalies, classify different types of galaxies, and even predict gravitational interactions that could lead to future mergers. In the case of Andromeda, machine learning is helping to uncover faint tidal streams. Gravitational wave detectors, such as LIGO and Virgo, have already detected ripples in spacetime caused by the mergers of black holes and neutron stars. Future gravitational wave observatories, like the proposed Laser Interferometer Space Antenna, or LISA, could detect signals from supermassive black holes at the centers of galaxies. If Andromeda's M31 star were to merge with another large black hole, it would produce detectable gravitational waves, providing a new way to study galactic interactions. Another promising method is neutrino astronomy, which detects nearly massless particles that pass through matter with ease. Neutrinos are produced in extreme environments, such as the cores of supernovae or around black holes. The IceCube Neutrino Observatory in Antarctica has already detected high-energy neutrinos from distant galaxies. If future detectors become more sensitive, they could reveal activity in Andromeda's core that is otherwise hidden from view. The continued development of space telescopes will further expand humanity's ability to study Andromeda and other distant galaxies. Concepts like the Habitable Worlds Observatory and the Large UV Optical Infrared Surveyor, or LUVOIR, could provide even sharper images and deeper observations. These next-generation observatories will search for planets around distant stars, examine the formation of galaxies, and detect signs of life beyond the Milky Way. Emerging theories, unanswered questions, and new horizons. One of the biggest mysteries is Andromeda's dark matter distribution. Like the Milky Way, Andromeda appears to be surrounded by an invisible halo of dark matter. Observations of Andromeda's satellite galaxies suggest that its dark matter halo might not be as uniform as expected. Some areas seem to have more dark matter than others, raising questions about how it is distributed and whether our current understanding of dark matter needs to be revised. Andromeda has a complex system of spiral arms, but they do not behave in the same way as those of the Milky Way. Some studies suggest that a past galactic interaction may have shaped these structures, while others propose that internal processes within the galaxy's disk caused them to form. Observations from telescopes like the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope aim to provide more detailed maps of Andromeda's spiral arms, potentially answering questions about how they developed over billions of years. The presence of an unusually high number of globular clusters in Andromeda also presents an ongoing mystery. Andromeda has over 500 known globular clusters, more than double the number found in the Milky Way. Some researchers believe that Andromeda's globular clusters may be remnants of ancient dwarf galaxies that were absorbed over time. Others suggest that Andromeda has been unusually efficient at forming such clusters. Studying their distribution and chemical composition may provide clues about the galaxy's past and how it built its stellar population. The core of Andromeda contains another puzzle, its supermassive black hole. This black hole is significantly larger than the one at the center of the Milky Way. Despite the two galaxies being similar in size, scientists do not yet know why Andromeda's black hole is so massive or how it has influenced the surrounding region. Future observations using radio telescopes and X-ray observatories may help clarify this mystery by studying the material falling into the black hole and the high-energy radiation it emits. The question of whether Andromeda has already begun interacting with the Milky Way is another open area of research. While the two galaxies will not fully collide for billions of years, some astronomers believe that their halos of gas and dark matter may already be overlapping. If true, this could mean that the early stages of their eventual merger are already underway. Future space telescopes will be able to analyze the movement of intergalactic gas more closely, looking for signs of interaction that could confirm or challenge this idea. Recent studies suggest that Andromeda may have experienced bursts of intense star formation in the past, followed by periods of relative inactivity. Some models propose that these bursts were triggered by past galactic encounters, while others suggest that they could be the result of internal processes. Mapping out the ages and compositions of stars across Andromeda's disk and halo may help piece together a clearer timeline of its formation. Galaxies are not isolated objects. They exist within a vast structure of filaments, voids, and clusters that make up the universe. Some researchers believe that Andromeda and the Milky Way are part of a larger structure known as the local sheet, a flattened arrangement of galaxies that extends for millions of light years. Studying Andromeda's motion and position within this structure could reveal how galaxies form and move within the broader universe. Some astronomers have suggested that studying Andromeda's rotation and mass distribution might offer insights into whether our understanding of gravity is complete. Alternative theories, such as modifications to Newtonian dynamics, attempt to explain certain galactic behaviors without relying on dark matter. If observations of Andromeda show inconsistencies with current models, it could spark new discussions about the nature of gravity itself. Alien architectures, megastructures in the Andromeda Galaxy. If an advanced alien civilization exists within the Andromeda Galaxy, its impact on the cosmos could be visible even from our distant vantage point. Megastructures, vast artificial constructions built on a scale far beyond anything humans have achieved, represent one of the most tantalizing possibilities in the search for extraterrestrial intelligence. These engineered marvels could reshape entire star systems, redirect energy on a galactic scale, or even manipulate space-time itself. While no confirmed evidence of such structures has been found, scientists continue to examine Andromeda with this possibility in mind, using observational techniques that might reveal the fingerprints of alien architecture. One of the most widely discussed types of megastructures is the Dyson sphere, a theoretical construct designed to capture and harness the energy output of a star. First proposed by physicist Freeman Dyson, such a structure could take many forms. A full Dyson sphere would completely encase a star, absorbing nearly all of its emitted light, while a Dyson swarm or Dyson ring would consist of many smaller satellites orbiting the star and collecting energy. If such structures exist in Andromeda, they might be detectable by looking for stars that appear dimmer than expected in visible light, but radiate an excess of infrared energy due to waste heat. Large-scale surveys using infrared telescopes, such as NASA's WISE, have scanned Andromeda's vast collection of stars, looking for anomalies that might indicate large-scale energy harvesting. While no clear evidence of a Dyson sphere has been found, researchers remain open to the possibility that future missions with more sensitive instruments could detect such structures. If an alien civilization has built a Dyson sphere or similar construct, it would signify an extraordinary level of technological advancement, possibly placing it among the most advanced civilizations in the universe. Beyond Dyson spheres, other hypothetical megastructures could exist in Andromeda, each serving a different purpose. A stellar engine, for example, is a theoretical construct designed to move an entire star system by directing its energy output in a specific direction. One proposed design, known as a Shkadov thruster, involves building a vast mirror that reflects a star's radiation asymmetrically, gradually pushing the star in a chosen direction. If such a structure were in use in Andromeda, it might reveal itself through the unusual motion of a star or group of stars that appear to be drifting in a way inconsistent with natural gravitational forces. Another possibility is the existence of artificial ringworlds, vast structures encircling a star at a distance similar to a habitable planet's orbit. Unlike a Dyson sphere, a ringworld would not enclose the star completely, but instead provide an immense habitable surface along its inner rim. Such a construct could offer far more living space than a natural planet, and might be detectable by its unusual light curve, as it would periodically block part of its star's light when viewed from Earth. If an advanced species in Andromeda has built such structures, their discovery would challenge current assumptions about the limits of engineering and planetary habitability. Some researchers have speculated about even more ambitious megastructures that could reshape entire regions of a galaxy. A Matryoshka brain, for example, is a theoretical construct consisting of multiple layers of Dyson-like energy collectors designed not just for power generation, but for advanced computation. This would effectively create a super-intelligent artificial mind on a colossal scale. If an advanced civilization in Andromeda has developed such a system, it might manipulate its surroundings in ways that could be detected from Earth. Unusual electromagnetic emissions, artificial pulses of radiation, or unexplained patterns in stellar motion might hint at the presence of such an intelligence. Galactic-scale engineering could extend even further. Some theorists have suggested the possibility of manipulating black holes, either for energy generation or for the creation of artificial wormholes to allow for faster-than-light travel. If such a civilization exists in Andromeda, its activities might be visible in the form of abnormal black hole behavior, perhaps unusual fluctuations in X-ray emissions, or jets of energy, directed in ways not typically seen in natural systems. The idea of civilizations harnessing the power of black holes is speculative, but it raises intriguing questions about the potential of life to shape the cosmos on vast scales. Another way to search for signs of alien megastructures in Andromeda is to look for objects that defy natural explanation. Large-scale radio surveys have already identified unusual signals from various regions of the universe, though none have been confirmed as artificial. Some researchers suggest that directed energy transmissions, perhaps signals used for interstellar communication or power transmission, could be detectable with sensitive radio telescopes. If Andromeda hosts an advanced civilization, it is possible that it has developed a network of artificial signals that could one day be intercepted by human instruments. Some scientists believe that a highly advanced civilization might leave behind subtle signatures rather than large, obvious structures. Instead of massive physical constructs, they might use advanced nanotechnology or even manipulate the very fabric of space-time. If an alien species in Andromeda has developed technology far beyond human comprehension, its presence might only be detected through its indirect effects on natural cosmic phenomena. Changes in the expected behavior of stars or unexplained fluctuations in cosmic microwave background radiation might hint at the influence of an advanced intelligence. If a megastructure is ever discovered in Andromeda, it would represent one of the most important scientific discoveries in history. It would prove that intelligent life is not only possible, but capable of reshaping the universe in extraordinary ways. Such a finding would force humanity to rethink its place in the cosmos, offering a glimpse of what might be possible for civilizations far older and more advanced than our own. Even if no megastructures are found, the search itself deepens our understanding of Andromeda and the broader universe, pushing the boundaries of what is known and inspiring future generations to continue exploring the mysteries of the cosmos. Cosmic rebirth, the re-emergence of life after galactic collisions. The collision between galaxies is often imagined as a scene of destruction, where stars are thrown from their orbits, entire systems are displaced, and the gravitational pull of merging structures reshapes the cosmos. But within this chaos, new opportunities emerge. The violent interaction between Andromeda and the Milky Way will not only tear apart old formations, but will also create regions where the conditions for life may begin anew. It is a process of transformation rather than outright annihilation, where the raw materials for new worlds are rearranged, igniting the possibility of life flourishing in unexpected places. As the two galaxies collide, vast clouds of gas will be compressed. This compression triggers an intense period of star formation, known as a starburst. These newborn stars will be surrounded by swirling disks of dust and gas, the building blocks of planetary systems. Some of these stars may form in stable environments where planets with suitable conditions for life could eventually take shape. Others may inherit worlds that have survived the cosmic upheaval, perhaps altered but still retaining the potential for habitability. If life already exists in one of these systems, it might endure the transition, adapting to its transformed surroundings. New planetary systems forming in the wake of a galactic collision will experience extreme conditions. The radiation levels will be high due to the abundance of young, hot stars emitting powerful stellar winds and intense ultraviolet light. However, this does not necessarily prevent life from taking hold. Some of the most resilient organisms on Earth thrive in extreme environments, from deep-sea hydrothermal vents to radiation-drenched landscapes. If similar conditions exist on newly formed planets, simple life forms might arise and persist, shielded beneath thick atmospheres, underground reservoirs, or deep within oceans. The gravitational chaos of a galactic merger will also dislodge entire planets from their host stars, sending them drifting into the void as rogue worlds. Though these planets would lack the warmth of a nearby sun, they may still harbor internal heat generated by radioactive decay or tidal forces. If they possess thick atmospheres or subsurface oceans insulated by layers of ice, they could sustain life even in the absence of a central star. The collision between Andromeda and the Milky Way may scatter these rogue planets across the newly merged galaxy, some of them potentially carrying microbial life on a journey through the dark depths of interstellar space. The immense forces at play will eject clouds of gas, dust, and organic molecules into new regions. These organic compounds, amino acids, complex hydrocarbons, and other precursors to life, will be spread across the galactic environment. If they land on newly forming planets or moons with the right conditions, they could seed the development of biological processes. Some scientists believe that life on Earth may have originated from such cosmic chemistry delivered by comets or asteroids rich in organic material. A galactic merger, with its widespread redistribution of matter, may enhance this process on a much larger scale. The Milky Way currently has a region known as the Galactic Habitable Zone, a band where conditions are neither too chaotic nor too barren for life to develop. After the merger, this habitable zone may shift as new star-forming regions emerge and older, more stable systems relocate. Some areas that were once inhospitable may find themselves in calmer environments where life has a greater chance of flourishing. Conversely, regions that once supported stable planetary systems may be disrupted, pushing potential life-bearing worlds into harsher conditions. Some planetary systems will remain relatively untouched by the chaos, continuing to orbit their host stars as they always have. If life exists on any of these worlds before the merger, it may survive the transition. Intelligent civilizations, if present, might face significant challenges in adapting to the changing galactic environment, but they may also benefit from new opportunities. A merger between galaxies could expose advanced species to new regions of space, potentially accelerating exploration, discovery, and even interstellar migration. Civilizations on the brink of collapse in one part of the galaxy may find refuge in another, carried along by the shifting cosmic tides. From destruction comes renewal. The violent dance of two galaxies merging will scatter old stars, forge new ones, and rearrange the structure of space on an immense scale. But through this chaos, life may find a way to begin again. Whether it emerges on newly formed planets, survives in hidden refuges, or travels between the stars on fragments of shattered worlds, the story of life in Andromeda and the Milky Way is far from over. The galaxy that forms from their union will be one of change, adaptation, and perhaps rebirth. And on that note of wonder, today's journey comes to an end. Leave a comment on what fascinates you about Andromeda. If you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.